A short account of the history of mathematics by W. W. Rouse Ball. Chapter 12, Part 2. The Mathematics of the Renaissance, 1450 to 1637. Part 2. Stifel. The methods used by Rudolf and Riese and their results were brought into general notice through Stifel's work, which had wide circulation in Germany. Michael Stifel, sometimes known by the Latin name of Stifelius, was born at Essling in 1486 and died at Jena in April 19th, 1567. He was originally an Augustine monk, but he accepted the doctrines of Luther, of whom he was a personal friend. He tells us in his algebra that his conversion was finally determined by noticing that Pope Leo X was the beast mentioned in the Revelation. To shew this, it was only necessary to add up the numbers represented by the letters in Leo Decimus. The M had to be rejected since it clearly stood for Mysterium, and the result amounts to exactly 10 less than 666, thus distinctly implying that it was Leo X. Luther accepted his conversion, but frankly told him that he had better clear his mind of any nonsense about the number of the beast. Unluckily for himself, Stifel did not act on this advice. Believing that he had discovered the true way of interpreting the biblical prophecies, he announced that the world would come to an end on October 3rd, 1533. The peasants of Holsdorf, of which place he was pastor, knowing of the scientific reputation, accepted his assurance on this point. Some gave themselves up to religious exercises, others wasted their goods in dissipation, but all abandoned their work. When the day foretold had passed, many of the peasants found themselves ruined. Furious at having been deceived, they seized the unfortunate prophet, and he was lucky in finding a refuge in the prison at Wittenberg, from which he was after some time released by the personal intercession of Luther. Stifel wrote a small treatise on algebra, but his chief mathematical work is his Arithmetica Integra, published at Nuremberg in 1544, with a preface by Melanchthon. The first two books of the Arithmetica Integra deal with surds and incommensurables, and are Euclidean in form. The third book is on algebra, and is noticeable for having called general attention to the German practice of using the signs plus and minus to denote addition and subtraction. There are faint traces of these signs being occasionally employed by Stifel as symbols of operation and not only as abbreviations. This application of them was apparently new. He not only employed the usual abbreviation for the Italian words which represent the unknown quantity and its powers, but in at least one case where there was several unknown quantities he represented them respectively by the letters A, B, C, and so on, thus reintroducing the general algebraic notation which had fallen into disuse since the time of Jordanus. It used to be said that Stifel was the real inventor of logarithms, but it is now certain that this opinion was due to a misapprehension of a passage in which he compares the geometrical and arithmetical progressions. Tartaglia. Niccolo Fontana, generally known as Nicholas Tartaglia, that is, Nicholas the Stammerer, was born at Brescia in 1500 and died in Venice in December 14th, 1557. After the capture of the town by the French in 1512, most of the inhabitants took refuge in the cathedral, and were then massacred by the soldiers. His father, who was a postal messenger at Brescia, was amongst the killed. The boy himself had his skull split through in 3 places, while both his jaws and his palate were cut open. He was left for dead, but his mother got into the cathedral, and finding him still alive managed to carry him off. Deprived of all resources, she recollected that dogs when wounded always lick the injured place, and to that remedy he attributed his ultimate recovery, but the injury to his palate produced an impediment in his speech, from which he received his nickname. His mother managed to get sufficient money to pay for his attendance at school for 15 days, and he took advantage of it to steal a copybook, from which he subsequently taught himself how to read and write. But so poor were they that he tells us that he could not afford to buy paper, and was thus obliged to make use of the tombstones as slates on which to work his exercises. He commenced his public life by lecturing at Verona, but he was appointed at some time before 1535 to a chair of mathematics at Venice, where he was living when he became famous, through his acceptance of a challenge from a certain Antonio de Fiori or Florido. Fiori had learnt from his master, one Scipione Ferreo, who died at Bologna in 1526, an empirical solution of a cubic equation of the form x cubed plus qx equals r. This solution was previously unknown in Europe, and it is probable that Ferreo had found the result in an Arab work. Tartaglia, in answer to a request from Colla in 1530, stated that he could effect a solution of a numerical equation of the form x cubed plus px squared equals r. Fiori, believing that Tartaglia was an impostor, challenged him to a contest. According to this challenge, each of them was to deposit a certain stake with the notary, and whoever could solve the most problems out of a collection of 30 propounded by the other was to get the stakes, 30 days being allowed for the solution of the questions proposed. Tartaglia was aware that his adversary was acquainted with the solution of a cubic equation of some particular form, and suspecting that the questions proposed to him would all depend on the solution of such a cubic equation, set himself the problem to find a general solution, and certainly discovered how to obtain a solution of some if not all cubic equations. His solution is believed to have depended on a geometrical construction, but led to a formula which is often but unjustly described as Cardan's. When the contest took place, all the questions proposed to Tartaglia were, as he had suspected, reducible to the solution of a cubic equation, and he succeeded within 2 hours in bringing them to a particular cases of the equation x cubed plus qx equals r, of which he knew the solution. His opponent failed to solve any of the problems proposed to him, which as a matter of fact were all reducible to numerical equations of the form x cubed plus px squared equals r. Tartaglia was therefore the conqueror. He subsequently composed some verses commemorative of his victory. The chief works of Tartaglia are as follows. His Nova Scienza, published in 1537. In this he investigated the fall of bodies under gravity, and he determined the range of a projectile, stating that it was a maximum when the angle of projection was 45 degrees. But this seems to have been a lucky guess. 2. An Arithmetic, published in 2 parts in 1556. 3. A Treatise on Numbers, published in 4 parts in 1560. And sometimes treated as a continuation of the arithmetic. In this he shewed how the coefficients of x in the expansion of 1 plus x to the power n could be calculated from those in the expansion of 1 plus x quantity to the power of n minus 1 for the cases where n is equal to 2, 3, 4, 5, or 6. It is possible that he also wrote a treatise on algebra and the solution of cubic equations, but if so, no copy is now extant. The other works were collected into a single edition and republished at Venice in 1606. The treatise on arithmetic and numbers is one of the chief authorities for our knowledge of the early Italian algorism. It is verbose, but gives a clear account of the different arithmetical methods then in use, and he has numerous historical notes which, as far as we can judge, are reliable, and are the authorities for many of the statements in the last chapter. It contains an immense number of questions on every kind of problem which would be likely to occur in mercantile arithmetic, and there are several attempts to frame algebraical formulae suitable for particular problems. These problems give incidentally a good deal of information as to the ordinary life and commercial customs of the time. Thus we find that the interest demanded on first class security in Venice ranged from 5 to 12% a year, while the interest on commercial transactions ranged from 20% a year upwards. Tartaglia illustrates the evil effects of the law forbidding usury by the manner in which it was evaded in farming. Farmers who were in debt were forced by their creditors to sell all their crops immediately after the harvest, the market being thus glutted. The price obtained was very low, and the moneylenders purchased the corn in the open market at an extremely cheap rate. The farmers then had to borrow their seed corn on condition that they replaced an equal quantity, or paid the then price of it, in the month of May when corn was dearest. Again, Tartaglia, who had been asked by the magistrates at Verona to frame for them a sliding scale by which the price of bread would be fixed by that of corn, enters into a discussion on the principles which it was then supposed should regulate it. In another place he gives the rules at that time current for preparing medicines. Pacioli had given in his arithmetic some problems of an amusing character, and Tartaglia imitated him by inserting a large collection of mathematical puzzles. He half apologizes for introducing them by saying that it was not uncommon at dessert to propose arithmetical questions to the company by way of amusement, and he therefore adds some suitable problems. He gives several questions on how to guess a number thought of by one of the company, or the relationships caused by the marriage of relatives, or difficulties arising from inconsistent bequests. Other puzzles are such as the following. There are 3 men, young, handsome, and gallant, who have 3 beautiful ladies for wives. All are jealous, as well as the husbands of the wives, as the wives of the husbands. They find on the bank of a river over which they have to pass a small boat which can hold no more than 2 persons. How can they pass so as to give rise to no jealousy? A ship carrying as passengers 15 Turks and 15 Christians encounters a storm, and the pilot declares that in order to save the ship and crew 1/2 of the passengers must be thrown into the sea. To choose the victims, the passengers are placed in a circle, and it is agreed that every 9th man shall be cast overboard, reckoning from a certain point. In what manner must they be arranged so that the lot may fall exclusively upon the Turks? 3 men robbed a gentleman of a vase containing 24 ounces of balsam. Whilst running away they met in a wood with a glass seller, of whom in a great hurry they purchased 3 vessels. On reaching a place of safety they wish to divide the booty, but they find that their vessels contain 5, 11, and 13 ounces respectively. How can they divide the balsam into equal portions? These problems, some of which are of oriental origin, form the basis of the collections of mathematical recreations by Bachet de Meziriac, Ozanam, and Montucla. Cardan. The life of Tartaglia was embittered by a quarrel with his contemporary Cardan, who, having under a pledge of secrecy obtained Tartaglia's solution of a cubic equation, and published it. Girolamo Cardan was born at Pavia on September 24, 1501, and died at Rome on September 21, 1576. His career is an account of the most extraordinary and inconsistent acts. A gambler, if not a murderer, he was also the ardent student of science, solving problems which had long baffled all investigation. At one time of his life he was devoted to intrigues which were a scandal even in the 16th century. At another he did nothing but rave on astrology, and yet at another he declared that philosophy was the only subject worthy of man's attention. His was the genius that was closely allied to madness. He was the illegitimate son of a lawyer of Milan, and was educated at the universities of Pavia and Padua. After taking his degree he commenced the life of a doctor, and practised his profession at Sacco and Milan from 1524 to 1550. It was during this period that he studied mathematics and published his chief works. After spending a year or so in France, Scotland, and England, he returned to Milan as a professor of science, and shortly afterwards was elected to a chair at Pavia. Here he divided his time between debauchery, astrology, and mechanics. His two sons were as wicked and passionate as himself. The elder was in 1560 executed for poisoning his wife, and about the same time Cardan in a fit of rage cut off the ears of the younger who had committed some offence. For this scandalous outrage he suffered no punishment, as the Pope Gregory XIII took him under his protection. In 1562 Cardan moved to Bologna, but the scandals connected with his name were so great that the university took steps to prevent his lecturing, and only gave way under pressure from Rome. In 1570 he was imprisoned for heresy on account of his having published the horoscope of Christ, and when released he found himself so generally detested that he determined to resign his chair. At any rate, he left Bologna in 1571 and shortly afterwards moved to Rome. Cardan was the most distinguished astrologer of his time, and when he settled at Rome he received a pension in order to secure his services as astrologer to the papal court. This proved fatal to him, for, having foretold that he should die on a particular day, he felt obliged to commit suicide in order to keep up his reputation, or so at least the story runs. The chief mathematical work of Cardan is the Ars Magna, published at Nuremberg in 1545. Cardan was much interested in the contest between Tartaglia and Fiori, and as he had already begun writing this book he asked Tartaglia to communicate his method of solving a cubic equation. Tartaglia refused, whereupon Cardan abused him in the most violent terms, but shortly afterwards wrote saying that a certain Italian nobleman had heard of Tartaglia's fame and was most anxious to meet him, and begged him to come to Milan at once. Tartaglia came, and though he found no nobleman awaiting him at the end of his journey, he yielded to Cardan's importunity and gave him the rule he wanted. Cardan on his side, taking a solemn oath that he would never reveal it, and would not even commit it to writing in such a way that after his death anyone could understand it. The rule is given in some doggerel verses which are still extant. Cardan asserts that he was given merely the result, and that he obtained the proof himself, but this is doubtful. He seems to have at once taught the method, and one of his pupils, Ferrari, reduced the equation of the fourth degree to a cubic, and so solved it. When the Ars Magna was published in 1545, the breach of faith was made manifest. Tartaglia was not unnaturally very angry, and after acrimonious controversy he sent a challenge to Cardan to take part in a mathematical duel. The preliminaries were settled, and the place of meeting was to be a certain church in Milan, but when the day arrived Cardan failed to appear, and sent Ferrari in his stead. Both sides claimed the victory, though I gather that Tartaglia was the more successful. At any rate his opponents broke up the meeting, and he was fortunate in escaping with his life. Not only did Cardan succeed in his fraud, but modern writers generally attribute the solution to him, so that Tartaglia has not even that posthumous reputation which is at least his due. The Ars Magna is a great advance on any algebra previously published. Hitherto algebraists had confined their attention to those roots of equations which were positive. Cardan discussed negative and even imaginary roots, and proved that the latter would always occur in pairs, though he declined to commit himself to any explanation as to the meaning of these sophistic quantities, which he said were ingenious though useless. Most of his analysis of cubic equations seemed to have been original. He shewed that if the three roots were real, Tartaglia's solution gave them in a form which involved imaginary quantities. Except for the somewhat similar researches of Bombelli a few years later, see below, page 231, that the theory of imaginary quantities received little further attention from mathematicians until Euler took the matter up after the lapse of nearly 2 centuries. Gauss first put the subject on a systematic and scientific basis, introduced the notation of complex variables, and used the symbol I to denote the square root of -1. The modern theory is chiefly based on his researches. Cardan found the relations connecting the roots with the coefficients of an equation. He was also aware of the principle that underlies Descartes' rule of signs, but as he followed the then general custom of writing his equations as the equality of two expressions, in each of which all the terms were positive, he was unable to express the rule concisely. He gave a method of approximating to the root of a numerical equation founded on the fact that if a function has opposite signs when two numbers are substituted on it, the equation obtained by equating the functions to 0 will have a root between those two numbers. Cardan's solution of a quadratic equation is geometrical and substantially the same as that given by Al-Khwarizmi. His solution of a cubic equation is also geometrical and may be illustrated by the following case, which he gives in chapter 11. To solve the equation x squared plus 6x equals 20, or any equation of the form x squared plus qx equals r, take two cubes such that the rectangle under their respective edges is 2 or 1/3 q, and the difference of their volumes is 20 or r. The x will be equal to the difference between the edges and the cubes. To verify this, he first gives a geometrical lemma to shew that if from a line AC a portion CB be cut off, then the cube on AB will be less than the difference between the cubes on AC and BC by 3 times the right parallelepiped, whose edges are respectively equal to AC, BC, and AB. This statement is equivalent to the algebraical identity a minus b quantity cubed equals a cubed minus b cubed minus 3ab multiplied by the quantity a minus b. And the fact that x satisfies the equation is then obvious. To obtain the lengths of the edges of the two cubes, he has only to solve a quadratic equation for which the geometrical solution previously given sufficed. Like all previous mathematicians, he gives separate proofs of his rule for the different forms of equations which can fall under it. Thus he proves the rule independently for equations of the form x cubed plus px equals q, x cubed equals px plus q, x cubed plus px plus q equals 0, and x cubed plus q equals px. It will be noticed that with geometrical proofs this was almost a necessity, but he did not suspect that the resulting formulae were general. The equations he considers are numerical, but in some of his analysis he uses literal coefficients. Shortly after Cardan came a number of mathematicians who did good work in developing the subject, who are hardly of sufficient importance to require a detailed mention here. Of these, the most celebrated are perhaps Ferrari and Rheticus. Ferrari. Ludovico Ferraro, usually known as Ferrari, whose name I have already mentioned in connection with the solution of a biquadratic equation, was born at Bologna on February 2, 1522, and died on October 5, 1565. His parents were poor, and he had taken into Cardan's service as an errand boy, but was allowed to attend his master's lectures and subsequently became the most celebrated pupil. He is described as a neat, rosy little fellow, with a bland voice, a cheerful face, and an agreeable short nose, fond of pleasure, of great natural powers, but with the temper of a fiend. His manners and numerous accomplishments procured him a place in the service of the Cardinal Ferrando Gonzaga, where he managed to make a fortune. His dissipations told on his health, and he retired in 1565 to Bologna, where he began to lecture on mathematics. He was poisoned the same year either by his sister, who seems to have been the only person for whom he had any affection, or by her paramour. Such work as he produced is incorporated in Cardan's Ars Magna or Bombelli's Algebra, but nothing can be definitely assigned to him except the solution of a biquadratic equation. Kola had proposed the solution of the equation x to the fourth plus 6x squared plus 36 equals 60x as a challenge to mathematicians. This particular equation had probably been found in some Arabic work. Nothing is known about the history of this problem except that Ferrari succeeded where Tartaglia and Cardan had failed. Rheticus. Georg Joachim Rheticus, born at Feldkirch in February 15, 1514, and died at Kaschau on December 4, 1576, was professor at Wittenberg and subsequently studied under Copernicus, whose works were produced under the direction of Rheticus. Rheticus constructed the various trigonometrical tables, some of which were published by his pupil Otho in 1596. These were subsequently completed and extended by Vieta and Pitiscus and are the basis of those still in use. Rheticus also found the values of sine of 2 theta and sine of 3 theta in terms of sine theta and cosine theta. I add here the names of some other celebrated mathematicians of about the same time, though their works are now of little value to any save antiquarians. Franciscus Maurolicus, born at Messina of Greek parents in 1494 and died in 1575, translated numerous Latin and Greek mathematical works and discussed the conics regarded as sections of a cone. His works were published at Venice in 1575. Jean Borel, born in 1492 and died at Grenoble in 1572, wrote an algebra founded on that of Stiefel and a history of the quadrature of the circle. His works were published at Lyons in 1559. Wilhelm Xylander, born at Augsburg on December 26, 1532, and died on February 10, 1576 at Heidelberg, where since 1558 he had been a professor, brought out an edition of the works of Psellus in 1556, an edition of Euclid's Elements in 1562, an edition of the Arithmetic of Diophantus in 1575, and some of the minor works which were collected and published in 1577. Federigo Comendino, born at Urbino in 1509 and died there on September 3, 1575, published a translation of the works of Archimedes in 1558, selections from Apollonius and Pappus in 1566, Euclid's Elements in 1572, and selections from Aristarchus, Ptolemy, Hero, and Pappus in 1574, all being accompanied by commentaries. Jacques Peltier, born at Le Mans on July 25, 1517, and died at Paris in July 1582, wrote several textbooks on algebra and geometry. Most of the results of Stiefel and Cardan are included in the former. Adrian Romanus, born at Louvain on September 29, 1561, and died on May 4, 1625, professor of mathematics and medicine at the University of Louvain, was the first to prove the usual formula for the sine of a plus b. And lastly, Bartholomeus Pitiscus, born on August 24, 1561, and died at Heidelberg, where he was professor of mathematics on July 2, 1613, published his Trigonometry in 1599. This contains the expression for the sine of a plus b and the sine of a minus b, and also the cosine of a plus b and the cosine of a minus b in terms of the trigonometrical ratios of a and b. About this time also several books were produced which, if they did not extend the boundaries of the subject, they systematized it. In particular I may mention those of Ramus and Bombelli. Ramus. Peter Ramus was born at Cuth in Picardy in 1515 and was killed at Paris in the massacre of St. Bartholomew on August 24, 1572. He was educated at the University of Paris, and on taking his degree he astonished and charmed the university with the brilliant declamation he delivered on the thesis that everything Aristotle had taught was false. He lectured, for it will be remembered that in the early days there were no professors, first at Le Mans and afterwards at Paris, and at the latter he founded the first chair of mathematics. Besides some works on philosophy, he wrote treatises on arithmetic, algebra, geometry, founded on Euclid, astronomy, founded on the works of Copernicus, and physics, which were long regarded on the continent as the standard textbooks on these subjects. They are collected in an edition of his works published at Bâle in 1569. Bombelli. Closely following the publication of Cardan's great work, Raffaello Bombelli published in 1572 an algebra which is a systematic exposition of what was then known on the subject. In the preface he alludes to Diophantus, who in spite of the notice of Regiomontanus was still unknown in Europe, and traces the history of the subject. He discusses radicals, real and imaginary. He treats the theory of equations and shews that in the irreducible case of a cubic equation the roots are all real, and he remarks that the problem to trisect a given angle is the same as that of the solution of the cubic equation. Finally, he gave a large collection of problems. Bombelli is chiefly distinguished in connection with the improvement of the notation of algebra which he introduced. The symbols then ordinarily used for the unknown quantity and its powers were letters which stood for the abbreviations of these words. Those most frequently adopted were R or Rj for radix or res x, Z or C for zensus or census x squared, C or K for cubus x cubed, etc. Thus x squared plus 5x minus 4 would have been written 1z p period 5r m period 4, where p stands for plus and m stands for minus. Xylander, in his edition of the Arithmetic of Diophantus in 1575, used other letters, and the symbols plus and minus would have been written in the above expressions thus: 1q plus 5n minus 4. A similar notation was sometimes used by Vieta and even by Fermat. The advance made by Bombelli was that he introduced a symbol like a semicircle holding a 1 above it, which I'll just call cup 1 for the unknown quantity, and cup 2 for its square, and cup 3 for its cubed, and so on, and therefore he wrote x squared plus 5x minus 4 as 1 cup 2 p period 5 cup 1 m period 4. Stevenius in 1586 employed 1 in a circle, 2 in a circle, and 3 inside a circle in a similar way, which I'll call circle 1, circle 2, circle 3, and suggested, though he did not use a corresponding notation for fractional indices, he would have written the above expression as 1 circle 2 plus 5 circle 1 minus 4 circle 0. But whether the symbols were more or less convenient, they were still only abbreviations for words, and were subject to all the rules of syntax. They merely afforded a sort of shorthand which the various steps and results could be expressed concisely. The next advance was the creation of symbolic algebra, and the chief credit of that is due to Vieta. The development of symbolic algebra. We have now reached a point beyond which any considerable development of algebra, so long as it was strictly syncopated, could hardly proceed. It is evident that Stifel and Bombelli and other writers of the 16th century had introduced, or were on the point of introducing, some of the ideas of symbolic algebra. But so far as the credit of inventing symbolic algebra can be put down to any one man, we may perhaps assign it to Vieta, while we may say that Harriot and Descartes did more than any other writers to bring it into the general use. It must be remembered, however, that it took time before all these innovations became generally known, and they were not familiar to the mathematicians until the lapse of some years after they had been published. End of section 17. Chapter 12, part 3. The Mathematics of the Renaissance, 1450 to 1637. Vieta. Franciscus Vieta, Francois Viete, born in 1540 at Fontenay near La Rochelle and died in Paris in 1603. He was brought up as a lawyer and practised for some time at the Parisian bar. He then became a member of the provincial parliament in Brittany, and finally in 1580 through the influence of the Duc de Rohan he was made Master of Requests, an office attached to the parliament at Paris. The rest of his life was spent in the public service. He was a firm believer in the divine right of kings, and possibly a zealous Catholic. After 1580 he gave up most of his leisure to mathematics, though his great work In Artem Analyticam Isagoge, in which he explained how algebra could be applied to the solution of geometrical problems, was not published till 1591. His mathematical reputation was already considerable when one day the ambassador from the Low Countries remarked to Henry IV that France did not possess any geometricians capable of solving a problem which had been propounded in 1593 by his countryman Adrian Romanus to all the mathematicians of the world, and which required the solution of an equation of the 45th degree. The king thereupon summoned Vieta and informed him of the challenge. Vieta saw that the equation was satisfied by a chord of a circle of unit radius which subtends an angle 2 pi over 45 at the centre, and in a few minutes he gave back to the king two solutions of the problem written in pencil. In explanation of this feat I should add that Vieta had previously discovered how to form the equation connecting sin n theta with sin theta and cos theta. Vieta in his turn asked Romanus to give the geometrical construction to describe a circle which should touch three given circles. This was the problem which Apollonius had treated in his De Tactionibus, a lost book which Vieta at a later time conjecturally restored. Romanus solved the problem with the aid of the conic sections, but failed to do it by Euclidean geometry. Vieta gave a Euclidean solution which so impressed Romanus that he travelled to Fontenay, where the French court was then settled, to make Vieta's acquaintance, an acquaintanceship which rapidly ripened into a warm friendship. Henry was much struck with the ability shewn by Vieta in this matter. The Spaniards had at the time a cipher containing nearly 600 characters, which was periodically changed, and which they believed to be impossible to decipher. A despatch having been intercepted, the king gave it to Vieta, and asked him to try to read it and find the key to the system. Vieta succeeded, and for 2 years the French used it greatly to their profit in the war which was then raging. So convinced was Philip II that the cipher could not be discovered, that when he found his plans known he complained to the Pope that the French were using sorcery against him, contrary to the practice of the Christian faith. Vieta wrote numerous works on algebra and geometry. The most important are In Artem Analyticam Isagoge, Tours 1591, the Supplementum Geometriae, and a collection of geometrical problems, Tours 1593, and the De Numerosa Potestatum Resolutione, Paris 1600. All of these were printed for private circulation only, but they were collected by F. van Schooten and published in one volume at Leyden in 1646. Vieta also wrote the De Equationum Recognitione et Emendatione, which was published after his death in 1615 by Alexander Anderson. The In Artem is the earliest work on symbolic algebra. It also introduced the use of letters for both known and unknown quantities, a notation for the powers of quantities, and enforced the advantage of working with homogeneous equations. To this an appendix called Logisti Speciosa was added on addition and multiplication of algebraical quantities and on the powers of a binomial up to the sixth. Vieta implies that he knew how to form the coefficients of these 6 expansions by means of the arithmetical triangle as Tartaglia had previously done. But Pascal was the first to give the general rule for forming it for any order, which is equivalent to saying that he could write down the coefficients of x in the expansion 1 plus x quantity to the power n if those in the expansion of 1 plus x quantity to the power n minus 1 were known. Newton was the first to give the general expression for the coefficient of x raised to the power p in the expansion of 1 plus x quantity to the power n. Another appendix known as the Tetica on the solution of equations was subsequently added to the In Artem. The In Artem is memorable for two improvements in algebraic notation which were introduced here, though it is probable that Vieta took the idea from both other authors. One of these improvements was that he denoted the known quantities by the consonants b, c, d, etc., and the unknown quantities by the vowels a, e, I, etc. Thus in any problem he was able to use a number of unknown quantities. In this particular point he seems to have been forestalled by Jordanus and Stifel. The present custom of using the letters at the beginning of the alphabet a, b, c to represent known quantities, and those toward the end x, y, z to represent the unknown quantities, was introduced by René Descartes in 1637. The other improvement was this. To this time it had been the custom to introduce new symbols to represent the square, cube, and so on of quantities which had already occurred in the equations. Thus if r or n stood for x, z, c, or q stood for x squared, and c or k for x cubed, etc. So long as this was the case, the chief advantage of algebra was that it afforded a concise statement of results, every statement of which was reasoned out. But when Vieta used a to denote the unknown quantity x, he sometimes employed a quadratus a cubus to represent x squared and x cubed, which at once shewed the connection between the different powers. And later the successive powers of a were commonly denoted by the abbreviations aq, ac, aqq, etc. Thus Vieta would have written the equation 3ba squared minus da plus a cubed equals z as b3 in a quadratur minus d plano in a plus a cubo equatur z solido. It will be observed that the dimensions of the constants b, d, and z are chosen so as to make the equation homogeneous. This is characteristic of all his work. It will also be noticed that he does not use a sign for equality. In fact, the particular sign equals, which we use to denote equality, was employed by him to represent the difference between. Vieta's notation is not so convenient as that previously used by Bombelli and Stevinus, but it was more generally adopted. Occasional instances of an approach to index notation, such as a to the power q, are said to occur in Vieta's works. These two steps were almost essential to any further progress in algebra. In both of them Vieta had been forestalled, but it was his good luck in emphasizing their importance to be the means of making them generally known at a time when opinion was ripe for such an advance. The De Equationem Recognitione et Emendatione is mostly on the theory of equations. Vieta here shewed that the first member of an algebraical equation, phi of x equals 0, could be resolved into linear factors, and explained how the coefficients of x could be expressed as functions of the roots. He also indicated how from a given equation another could be obtained whose roots were equal to those of the original, increased by a given quantity or multiplied by a given quantity, and he used this method to get rid of the coefficients of x in a quadratic equation and of the coefficient of x squared in a cubic equation, and was thus enabled to give the general algebraic solution of both. His solution of a cubic equation is as follows. First, reduce the equation to the form x cubed plus 3a squared x equals 2b cubed. Next, let x equal a squared over y minus y, and we get y to the sixth plus 2b cubed y cubed equals a to the sixth, which is a quadratic in y cubed. Hence y can be found, and therefore x can be determined. His solution of a biquadratic is similar to that known as Ferrari's. He first got rid of the term involving x cubed, thus reducing the equation to the form x to the fourth plus a squared x squared plus b cubed x equals c to the power 4. He then took the terms involving x squared and x to the right hand side of the equation and added x squared y squared plus a quarter y to the fourth to each side, so that the equation became quantity x squared plus half y squared all squared equals x squared multiplied by the quantity y squared minus a squared, subtract b cubed x plus a quarter y to the fourth plus c to the fourth. He then chose y so that the right hand side of this equality is a perfect square. Substituting this value of y, he was able to take the square root of both sides and thus obtain two quadratic equations for x, each of which can be solved. The De Numerosa Potestatem Resolutione deals with the numerical equations. In this a method of approximating to the values of positive roots is given, but it is prolix and of little use, though the principle, which is similar to that of Newton's rule, is correct. Negative roots are uniformly rejected. This work is hardly worthy of Vieta's reputation. Vieta's trigonometrical researches are included in various tracts which are collected in Schutten's edition. Besides some trigonometrical tables, he gave the general expression for the sine or chord of an angle in terms of the sine and cosine of its submultiples. Delambre considers this as the completion of the Arab system of trigonometry. We may take it then that from this time the results of elementary trigonometry were familiar to mathematicians. Vieta also elaborated the theory of right-angled spherical triangles. Among Vieta's miscellaneous tracts will be found a proof that each of the famous geometrical problems of the trisection of an angle and the duplication of the cube depends on the solution of a cubic equation. There are also some papers connected with an angry controversy with Clavius in 1594 on the subject of the reformed calendar, in which Vieta was not well advised. Vieta's works on geometry are good, but they contain nothing which requires mention here. He applied algebra and trigonometry to help him in investigating the properties of figures. He also, as I have already said, laid great stress on the desirability of always working with homogeneous equations, so that if a square or a cube were given it should be denoted by expressions like a squared or b cubed, but not by terms like m or n which do not indicate the dimensions of the quantities they represent. He had a lively dispute with Scaliger on the latter publishing a solution of the quadrature of the circle, and succeeded in shewing the mistake into which his rival had fallen. He gave a solution of his own which as far as it goes is correct, and stated that the area of a square is to that of the circumscribing circle as the square root of a half times the square root of the quantity a half plus the square root of a half multiplied by the quantity in brackets the square root of a half plus the quantity square root of a half plus the square root of a half end of quantity ad infinitum. This is one of the earliest attempts to find the value of pi by means of an infinite series. He was well acquainted with the extant writings of the Greek geometricians, and introduced the curious custom, which during the 17th and 18th centuries became fashionable, of restoring lost classical works. He himself produced a conjectural restoration of De Tactionibus of Apollonius. Girard. Vieta's results in trigonometry and the theory of equations were extended by Albert Girard, a Dutch mathematician who was born in Lorraine in 1590 and died in 1633. In 1626 Girard published at The Hague a short treatise on trigonometry, to which were appended tables of the values of the trigonometrical functions. This work contains the earliest use of the abbreviations sin, sin, tan, tan, and sec, sec, for sine, tangent, and secant. The supplemental triangles in a spherical trigonometry are also discussed, and seem to have been discovered by Girard independently of Vieta, and he also gave the expression for the area of the spherical triangle in terms of the spherical excess. This was discovered independently by Calivari. In 1627 Girard brought out an edition of Malraux's geometry with considerable additions. Girard's chief discoveries are contained in his Invention nouvelle en algèbre, published at Amsterdam in 1629. This contains the earliest use of brackets, a geometrical interpretation of the negative sign, the statement that the number of roots in an algebraical equation is equal to its degree, the distinct recognition of imaginary roots, and probably implies also a knowledge that the first member of an algebraical equation phi of x equals 0 could be resolved into linear factors. Girard's researches were unknown to most of his contemporaries and exercised no appreciable influence on the development of mathematics. The invention of logarithms by Napier of Merchistown in 1614 and their introduction into England by Briggs and others have already been mentioned in chapter 11. Napier. John Napier was born in Merchistown in 1550 and died on April 4, 1617. He spent most of his time on the family estate near Edinburgh and took an active part in the political and religious controversies of the day. The business of his life was to shew that the Pope was the Antichrist, but his favourite amusement was the study of mathematics and science. As soon as the use of exponents became common in algebra, the introduction of logarithms would naturally follow, but Napier reasoned out that the result without the use of any symbolic notation to assist him, and the invention of logarithms was so far from being a sudden inspiration that it was the result of efforts of many years with a view to abbreviate the processes of multiplication and division. It is likely that Napier's attention may have been partly directed to the desirability of facilitating computations by the stupendous arithmetical efforts of some of his contemporaries, who seem to have taken a keen pleasure in surpassing one another in the extent to which they carried out multiplications and divisions. The trigonometrical tables by Rheticus, which were published in 1596 and 1613, were calculated in a most laborious way. Vieta himself delighted in arithmetical calculations which must have taken hours or days of hard work, and of which the results often served no useful purpose. L. van Keulen (1539 1610) practically devoted his life to finding a numerical approximation to the value of pi, finally in 1610 obtaining it correct to 35 places of decimals, while, to cite one more instance, P. A. Cataldi (1548 1626), who is chiefly known for his invention in 1613 of the form of continued fractions, though he failed to establish any of their properties, must have spent years in numerical calculations. In regard to Napier's other work, I may again mention that in his Rhabdologia, published in 1617, he introduced an improved form of rod by the use of which the product of two numbers can be found in a mechanical way. They can also be used for finding the quotient of one number by another. He also invented two other rods called virgulae, by which the square and the cube roots can be extracted. I should add that in spherical trigonometry he discovered certain formulae known as Napier's analogies, and also enunciated a rule of circular parts for the solution of right-angled spherical triangles. Briggs. The earliest table of common logarithms was constructed by Briggs and published in 1617. Henry Briggs was born near Halifax in 1556. He was educated at St. John's College, Cambridge, and took his degree in 1581 and obtained a fellowship in 1588. He was elected to the Gresham Professorship of Geometry in 1594, and in 1619 became Savilian Professor at Oxford, a chair which he held until his death on January 26, 1631. It may be interesting to add that the chair of geometry founded by Sir Thomas Gresham in 1596 was the earliest professorship of mathematics established in Great Britain. Some 20 years earlier Sir Henry Savile had given at Oxford open lectures on Greek geometry and geometricians, and in 1619 he endowed the chairs of geometry and astronomy in that university which are still associated with his name. Both in London and at Oxford, Briggs was the first occupant of the chair of geometry. He began his lectures at Oxford with the ninth proposition of the first book of Euclid, that being the furthest point to which Savile had been able to carry his audiences. At Cambridge the Lucasian chair was established in 1663, the earliest occupants being Barrow and Newton. The almost immediate adoption through Europe of logarithms for astronomical and other calculations was mainly the work of Briggs. Amongst others he convinced Kepler of the advantages of Napier's discovery, and the spread of the use of logarithms was rendered more rapid by the zeal and reputation of Kepler, who by his tables of 1625 and 1629 brought them into vogue in Germany, while Cavalieri in 1624 and Edmund Wingate in 1626 did similar service for Italian and French mathematicians respectively. Harriot. Thomas Harriot, born at Oxford in 1560 and died in London on July 2, 1621, did a great deal to extend and codify the theory of equations. The early part of his life was spent in America with Sir Walter Raleigh. While there he made the first survey of Virginia and North Carolina, the maps of these being subsequently presented to Queen Elizabeth. On his return to England he settled in London and gave up most of his time to mathematical studies. The majority of the propositions I have assigned to Vieta are to be found in Harriot's writings, but it is uncertain whether they were discovered by him independently of Vieta or not. In any case it is probable that Vieta had not fully realized all that was contained in the propositions he had enunciated. The full consequences of these, with numerous extensions and systematic exposition of the theory of equations, were given by Harriot in his Artis Analyticae Praxis, which was first printed in 1631. The Praxis did not differ essentially from a good modern textbook. It is far more analytical than any algebra that preceded it, and marks a great advance in both symbolism and notation. It was widely read and proved one of the most powerful instruments in bringing analytical methods into general use. Harriot was, I believe, the earliest writer who realized the advantage to be obtained by taking all of the terms of an equation to one side of it. He was the first to use angle bracket signs to denote greater than and less than. When he denoted the unknown quantity by a, he represented a squared by a cubed by aaa, and so on. This is a distinct improvement on Vieta's notation. The same symbolism was used by Wallis as late as 1685, but concurrently with the modern index notation which was introduced by Descartes. Extracts from some of the other writings of Harriot were published by Rigaud in 1833. Oughtred. Among those who contributed to the general adoption in England of those various improvements and additions to algorism and algebra was William Oughtred, who was born at Eton on March 5, 1574, and died at his vicarage of Albury in Surrey on June 30, 1660. It is usually said that the cause of his death was the excitement and delight which he experienced at hearing the House of Commons had voted the king's return. But a recent critic adds that it should be remembered that by way of excuse that he, Oughtred, was then 86 years old. Oughtred was educated at Eton and King's College, Cambridge, of the latter of which colleges he was a fellow and for some time a mathematical lecturer. His Clavis Mathematica, published in 1631, is a good systematic textbook on arithmetic, and it contains practically all that was then known on the subject. In this work he introduced the symbol times for multiplication, and the symbol double colon in proportion. Previously to this time a proportion such as a colon b equals c colon d was usually written as a minus sign b minus sign c minus sign d, but he denoted it by a dot b colon colon c dot d. Wallace says that some found fault with the book on account of the style, but that they only displayed their own incompetence, for Oughtred's words would be always full but not redundant. Pell makes a somewhat similar remark. Oughtred also wrote a treatise on trigonometry published in 1657, in which abbreviations for sine, cosine, etc. were employed. This was really an important advance, but the works of Girard and Oughtred in which they were used were neglected and soon forgotten, and it was not until Euler reintroduced the contractions for the trigonometrical functions that they were generally adopted. We may say roughly that henceforth elementary arithmetic, algebra, and trigonometry were treated in a manner which is not substantially different from that now in use, and that the subsequent improvements introduced were additions to the subjects then known, and not a rearrangement of them on new foundations. The origins of the more common symbols in algebra. It may be convenient if I collect here in one place the scattered remarks I have made on the introduction of the various symbols of the more common operations in algebra. The latter Greeks and the Hindus and Jordanus indicated addition by mere juxtaposition. It will be observed that this is still the custom in arithmetic, where for example 2 1/2 stands for 2 plus 1/2. The Italian algebraists, when they gave up expressing every operation in words at full length, and introduced syncopated algebra, usually denoted plus by its initial letter p, or a line being sometimes drawn through the letter to shew that it was a symbol of operation and not a quantity, but the practice was not uniform. Pacioli, for example, sometimes denoted it by p with a bar on top, and sometimes by e, and Tartaglia commonly denoted it by the Greek letter phi. The German and English algebraists, on the other hand, introduced the sign plus almost as soon as they used algorism, but they spoke of it as signum additorem and employed it only to indicate excess. They also used it in the sense referred to previously. Widman used it as an abbreviation for excess in 1489. By 1630 it was part of the recognized notation of algebra and was used as a symbol of operation. Subtraction was indicated by Diophantus as an inverted and truncated Greek letter phi. The Hindus denoted it by a dot. The Italian algebraists, when they introduced syncopated algebra, generally denoted minus by m, big capital M or lowercase m, a line being sometimes drawn through the letter, but the practice was not uniform. Pacioli, for example, denoting it sometimes by m with a bar over it, and sometimes by de for demptus. The German and English algebraists introduced the present symbol by which they described signum subtractorum. It is most likely that the vertical bar in the symbol for plus was superimposed on the symbol for minus to distinguish the two. In origin both symbols were probably mercantile marks. It may be noticed that Pacioli and Tartaglia found the sign minus already used to denote a division, a ratio, or a proportion indifferently. The present sign was in general use by about the year 1630 and was then employed as a symbol of operation. Oughtred in 1631 used the sign times to denote multiplication. Harriot in 1631 denoted the operation by a dot. Descartes in 1637 indicated it by juxtaposition. I am not aware of any symbols for it which were in previous use. Leibniz in 1686 employed the sign an inverted semicircle facing down to denote multiplication, and a semicircle facing up to denote division. Division was ordinarily denoted by the Arab way of writing quantities in the form of a fraction by means of a line drawn between them in any of the forms a minus b, a/b, or a over b. Oughtred in 1631 employed a dot to denote either division or a ratio. I do not know when the colon was first introduced to denote a ratio, but it occurs in a work by Clairaut published in 1760. I believe that the then current symbol for division, with a dash inside a colon, is only a combination of the dash and the colon. It was used by John Hendrik Rahn at Zurich in 1659 and John Pell in London in 1668. The current symbol for equality was introduced by Record in 1557. Xylander in 1575 denoted it by two parallel vertical lines, but in general till the year 1600 the word was written at length, and from then until the time of Newton, say about 1680, it was more frequently represented by an alpha or a reverse alpha than by any other symbol. Each of these latter signs were used as a contraction for the first two letters of the word aequalis. I may add that Vieta, Schouten, and others employed the sign equals to denote the difference between. Thus a equal sign b meant with them what we denote by a minus b. The symbol double colon to denote proportion or by the equality of two ratios was introduced by Oughtred in 1631 and it was brought into common use by Wallis in 1686. There is no object in having a symbol to indicate equality of two ratios which is different from that used to indicate equality of other things, and it is better to replace it by the sign equals. The sign right angle bracket for is greater than and the sign left angle bracket for is less than were introduced by Harriot in 1631, but Oughtred simultaneously invented different symbols for greater than, less than, and these latter were frequently used until the beginning of the 18th century, e.g. by Barrow. The symbol equal sign with a stroke through it for is not equal to, a right angle bracket with a stroke through it for is not greater than, and a left angle bracket with a stroke through it for is not less than, are of recent introduction. The vinculum was introduced by Vieta in 1591, and the brackets were first used by Girard in 1629. The different methods of representing the power to which a magnitude was raised have already been briefly alluded to. The earliest known attempt to frame a symbolic notation was made by Bombelli in 1572 when he represented an unknown quantity by 1 inside an upturned semicircle, and its square by 2 inside an upturned semicircle, and its cube by a 3 inside an upturned semicircle, etc. In 1586 Stevinus used 1 written inside a circle, 2 written inside a circle, 3 written inside a circle in a similar way, and suggested, though he did not use a corresponding notation for fractional indices. In 1591 Vieta improved on this by denoting the different powers of a by a quad, a cub, etc., so that he could indicate the powers of different magnitudes. Harriot in 1631 further improved on Vieta's notation by writing AA for a squared, AAA for a cubed, etc., and this remained in use for 50 years concurrently with the index notation. In 1634 P. Herragonus in his Cursus Mathematicus, published in 5 volumes at Paris in 1634 to 1637, wrote A2, A3 for a squared, a cubed. The symbol surd to denote the square root was first introduced by Rudolph in 1526. A similar notation had been used by Bhaskara. The idea of using exponents to mark the power to which a quantity was raised was due to Descartes, and was introduced by him in 1637, but he used only positive integral indices, a to the 1, a squared, a cubed, and so on. Wallis in 1659 explained the meaning of negative fractional indices in expressions such as x to the power of -1 or x to the power of 2/3, etc., the latter conception having been foreshadowed by Erasmus and perhaps by Stevinus. Finally, the idea of an index unrestricted in magnitude, such as the n in the expansion of a to the power n, I believe is due to Newton and was introduced by him in connection with the binomial theorem in the letters for Leibniz written in 1676. The symbol 8 written sideways for infinity was first employed by Wallis in 1655 in his Arithmetica Infinitorum, but does not occur again until 1713 when it is used in James Bernoulli's Ars Conjectandi. The sign was sometimes employed by the Romans to denote the number 1000, and it has been conjectured that this led to its being applied to represent any very large number. There are but few special symbols in trigonometry. I may however add here the following note which contains all that I have been able to learn on the subject. The current sexagesimal division of angles is derived from the Babylonians through the Greeks. The Babylonian unit angle was the angle of an equilateral triangle. Following their usual practice, this was divided into 60 equal parts or degrees. A degree was subdivided into 60 equal parts or minutes, and so on. The word sine was used by Regiomontanus and was derived from the Arabs. The terms secant and tangent were introduced by Thomas Finck, born in Denmark in 1561 and died in 1646, in his Geometriae Rotundae, Bale 1583. And the word cosecant, I believe, was first used by Rheticus in his Opus Palatinum 1596. The terms cosine and cotangent were first employed by E. Gunter in his Canon Triangularum, London 1620. The abbreviations sin, tan, sec for secant were used in 1626 by Albert Gerard, and those of cos, cos, and cot for cotangent by Oughtred in 1657. But these contractions did not come into general use till Euler reintroduced them in 1748. The idea of trigonometrical functions originated with John Bernoulli, and this view of the subject was elaborated in 1748 by Euler in his Introductio in Analysen Infinitorum. End of section 16. Chapter 13. The close of the Renaissance, circa 1586 to 1637. The closing years of the Renaissance were marked by a revival of interest in nearly all branches of mathematics and science. As far as pure mathematics is concerned, we have already seen that during the last half of the 16th century there had been a great advance in algebra, theory of equations, and trigonometry. And we shall shortly see in the second section of this chapter that in the early part of the 17th century some new processes in geometry were invented. If, however, we turn to applied mathematics, it is impossible not to be struck by the fact that even as late as the middle or end of the 16th century no marked progress in the theory had been made from the time of Archimedes. Statics of solids and hydrostatics remained in much the state in which he had left them, while dynamics as a science did not exist. It was Stevinus who gave us the first impulse to the renewed study of statics, and Galileo who laid the foundation of dynamics, and to their works the first section of this chapter is devoted. The development of mechanics and experimental methods. Stevinus. Simon Stevinus was born in Bruges in 1548 and died at The Hague in the 17th century. We know very little of his life save that he was originally a merchant's clerk at Antwerp, and at a later period of his life was the friend of Prince Maurice of Orange, by whom he was made quartermaster general of the Dutch army. To his contemporaries he was the best known for his works on fortifications and military engineering, and the principles he laid down are said to be in accordance with those which are now usually accepted. To the general populace he was also well known on account of his invention of a carriage which was propelled by sails. This ran on the seashore, carried 28 people, and easily outstripped horses galloping by the side. His model of it was destroyed in 1802 by the French when they invaded Holland. It was chiefly owing to the influence of Stevinus that the Dutch and French began a proper system of bookkeeping in the national accounts. I have already alluded to the introduction in his Arithmetic, published in 1585, of exponents to mark the power to which quantities were raised. He is said to have suggested the use of fractional but not negative exponents. For instance, he wrote 3x squared minus 5x plus 1 as 3 followed by 2 in a circle for x squared minus 5 followed by a 1 in a circle signifying x plus 1 followed by a solid dot in a circle. His notation for decimal fractions was of a similar character. In the same book he likewise suggested a decimal system of weights and measures. He also published a geometry which is ingenious, though it does not contain many results which were not previously known. It is however on his Statics and Hydrostatics, published in Flemish at Leyden in 1586, that his fame will rest. In this work he enunciated the triangle of forces, a theorem which some think was the first propounded by Leonardo da Vinci. Stevinus regarded this as the fundamental proposition of the subject. Previous to the publication of his work the science of statics had rested on the theory of the lever, but since then it has been usual to commence by proving the possibility of representing forces by straight lines, and so of reducing many theorems to geometrical propositions, and in particular to obtaining in that way a proof of the parallelogram, which is equivalent to the triangle of forces. Stevinus is not clear in his arrangement of the various propositions and discussions of their sequence, and the new treatment of the subject was not definitely established before the appearance in 1687 of Varignon's work on mechanics. Stevinus also found the force which must be exerted along the line of the greatest slope to support a given weight on an inclined plane, a problem the solution of which had long been in dispute. He further distinguished between stable and unstable equilibrium. In hydrostatics he discussed the question of the pressure which a fluid can exercise, and explained the so-called hydrostatic paradox. Stevinus was somewhat dogmatic in his statements and allowed no one to differ from his conclusions. And those, says he in one place, who cannot see this, may the author of nature have pity upon their unfortunate eyes, for the fault is not in the thing, but in the sight which we are not able to give them. Galileo. Just as the modern treatment of statics originates with Stevinus, so the foundation of the science of dynamics is due to Galileo. Galileo Galilei, born in Pisa on February 18, 1564, and died near Florence on January 8, 1642. His father, a poor descendant of an old and noble Florentine house, was himself a fair mathematician and a good musician. Galileo was educated at the monastery in Vallombrosa, where his literary ability and mechanical ingenuity attracted considerable attention. He was persuaded to become a novitate of the order in 1580, but his father, who intended him to be a doctor, at once removed him and sent him in 1581 to the University of Pisa to study medicine. It was there that he noticed that the great bronze lamp which still hangs from the roof of the cathedral performed its oscillations in equal times, quite independently of whether the oscillations were large or small, a fact which he verified by counting his pulse. He had been hitherto purposely kept in ignorance of mathematics, but one day, by chance hearing a lecture on geometry, he was so fascinated by the science that he thenceforward devoted all of his spare time to its study, and finally he got leave to discontinue his medical studies. He left university in 1586 and almost immediately commenced his original researches. He published in 1587 an account of the hydrostatic balance, and in 1588 an essay on the centre of gravity in solids. The fame of these works secured for him the appointment to the mathematical chair at Pisa, the stipend, as was the case with most professorships, being very small. During the next 3 years he carried on from the Leaning Tower that series of experiments on falling bodies which established the first principles of dynamics. Unfortunately, the manner in which he promulgated his discoveries and the ridicule he threw on those who opposed him gave not an unnatural offence, and in 1591 he was obliged to resign his position. At this time he seems to have been much hampered by want of money. Influence was however exerted on his behalf with the Venetian Senate, and he was appointed professor at Padua, a chair which he held for 18 years, 1592 to 1610. His lectures there seem to have been chiefly on the mechanics and hydrostatics, and the substance of them is contained in his treatise on mechanics, which was published in 1612. In these lectures he repeated his Pisan experiments and demonstrated that falling bodies did not, as was then believed, descend with velocities proportional, amongst other things, to their weights. He further shewed that, if it were assumed that they were descended with a uniformly accelerated motion, it was possible to deduce the relations of connecting velocity, space, and time, which did actually exist. At a later date, by observing the times of descent of bodies sliding down inclined planes, he shewed that this hypothesis was true. He also proved that the path of a projectile was a parabola, and in doing so implicitly used the principles laid down in the first 2 laws of motion as enunciated by Newton. He gave an accurate definition of momentum, which some writers have thought may be taken to imply a recognition of the truth of the third law of motion. The laws of motion are however nowhere enunciated in the precise and definite form, and Galileo must be regarded rather as preparing the way for Newton than as being himself the creator of the science of dynamics. In statics he laid down the principle that in machines what was gained in power was lost in speed, and in the same ratio. In the statics of solids he found the force which can support a given weight on an inclined plane. In hydrostatics he propounded the more elementary theorems on pressure and on floating bodies, while among hydrostatical instruments he invented the thermometer, though in a somewhat imperfect form. It is, however, as an astronomer that most people regard Galileo, and though strictly speaking his astronomical researches lie outside the subject matter of this book, it may be interesting to give the leading facts. It was in the spring of 1609 that Galileo heard that a tube containing lenses had been made by Lippershey in Holland, which served to magnify objects seen through it. This gave him the clue, which he constructed a telescope of that kind which still bears his name, and of which an ordinary opera glass is an example. Within a few moments he had produced instruments which were capable of magnifying 32 diameters, and within a year he had made and published observations on the solar spots, the lunar mountains, Jupiter's satellites, the phases of Venus, and Saturn's ring. Honours and emoluments were showered on him, and he was enabled in 1610 to give up his professorship and retire to Florence. In 1611 he paid a temporary visit to Rome, and exhibited in the gardens of the Vatican the new worlds revealed by the telescope. It would seem that Galileo had always believed in the Copernican system, but was afraid of promulgating it on account of the ridicule it excited. The existence of Jupiter's satellites seemed however to make this truth almost certain, and he now boldly preached it. The orthodox party resented his action, and on February 24, 1616, the Inquisition declared that to suppose the sun the centre of the solar system was absurd, heretical, and contrary to Holy Scripture. The edict of March 5, 1616, which carried this into effect, had never been repealed, though it has long been tacitly ignored. It is well known that toward the middle of the 17th century the Jesuits evaded it by treating the theory as an hypothesis from which, though false, certain results would follow. In January 1632 Galileo published his dialogues on the system of the world, in which in clear and forcible language he expounded the Copernican theory. In these, apparently through jealousy of Kepler's fame, he does not so much as mention Kepler's laws, the first two of which had been published in 1609 and the third in 1619, and he rejects Kepler's hypothesis that the tides are caused by the attraction of the moon. He rests the proof of the Copernican hypothesis on the absurd statement that it would cause tides because different parts of the earth would rotate with different velocities. He was more successful in shewing that mechanical principles would account for the fact that a stone thrown straight up would fall again to the place from which it was thrown, a fact which had previously been one of the chief difficulties in the way of any theory which supposed the earth to be in motion. The publication of this book was certainly contrary to the edict of 1616. Galileo was at once summoned to Rome, forced to recant, do penance, and was only released on good behaviour. The documents recently printed shew that he was threatened with the torture, but that there was no intention of carrying the threat into effect. When released he again took up his work on mechanics, and by 1636 had finished a book which was published under the title Discorsi intorno ad nuove scienze at Leyden in 1638. In 1637 he lost his sight, but with the aid of pupils he continued his experiments on mechanics and hydrostatics, and in particular on the possibility of using a pendulum to regulate a clock, and on the theory of impact. An anecdote of this time has been preserved which may or may not be true, but is sufficiently interesting to bear repetition. According to one version of the story, Galileo was one day interviewed by some members of a Florentine guild who wanted their pumps altered so as to raise water to a height which was greater than 30 feet, and thereupon he remarked it might be desirable to first find out why the water rose at all. A bystander interfered and said there was no difficulty about that because nature abhorred a vacuum. Yes, said Galileo, but apparently it is only a vacuum which is less than 30 feet. His favourite pupil Torricelli was present, and thus had his attention directed to the question, which he subsequently elucidated. Galileo's work may, I think, be fairly summed up by saying that his researches on mechanics are deserving of high praise, and that they are memorable for clearly enunciating the fact that science must be founded on laws obtained by experiment. His astronomical observations and his deductions therefrom were also excellent, and were expounded with a literary and scientific skill which leaves nothing to be desired. But though he produced some of the evidence which placed the Copernican theory on a satisfactory basis, he did not himself make any special advance in the theory of astronomy. Francis Bacon. The necessity of an experimental foundation for science was advocated with even greater effect by Galileo's contemporary Francis Bacon, Lord Verulam, who was born in London on January 22, 1561, and died on April 9, 1626. He was educated at Trinity College, Cambridge. His career in politics and at the bar culminated in his becoming Lord Chancellor with the title Lord Verulam. The story of his subsequent degradation for accepting bribes was well known. His chief work is the Novum Organum, published in 1620, which he lays down the principles which should guide those who are making experiments on which they propose to find a theory of any branch of physics or applied mathematics. He gave rules by which the results of induction could be tested, hasty generalizations avoided, and experiments used to check one another. The influence of this treatise in the 18th century was great, but it is probable that during the preceding century it was little read, and the remark repeated by several French writers that Bacon and Descartes are the creators of modern philosophy rests on a misapprehension of Bacon's influence on his contemporaries. Any detailed account of this book belongs, however, to the history of scientific ideas rather than to that of mathematics. Before leaving the subject of applied mathematics, I may add a few words on the writings of Guldinus, Wright, and Snell. Guldinus. Habakkuk Guldinus, born in St. Gall on June 12, 1577, and died at Graz, November 3, 1643, was of Jewish descent, but was brought up as a Protestant. He was converted to Roman Catholicism and became a Jesuit when he took the Christian name of Paul, and it was to him that the Jesuit colleges in Rome and Graz owed their mathematical reputation. The two theorems known by the name of Pappus, to which I alluded, were published by Guldinus in the fourth book of his De Centro Gravitatis, Vienna, 1635–1642. Not only were the rules in question taken without acknowledgment from Pappus, according to Montecle, the proof of them was given by Guldinus was faulty, even though he was successful in applying them to the determination of the volumes and surfaces of certain solids. The theorems were however previously unknown, and their enunciation excited considerable interest. Wright. I may here also refer to Edward Wright, who is worthy of mention for having put the art of navigation on a scientific basis. Wright was born in Norfolk at about 1560 and died in 1615. He was educated at Caius College, Cambridge, of which society he was subsequently a fellow. He seems to have been a good sailor, and he has special talent for the construction of instruments. About 1600 he was elected lecturer on mathematics by the East India Company. He then settled in London and shortly afterwards was appointed mathematical tutor to Prince Henry of Wales, the son of James I. His mechanical ability may be illustrated by an orrery of his construction, by which it was possible to predict eclipses for over 17,000 years in advance. It was shewn in the Tower as a curiosity as late as 1675. In the maps in use before the time of Gerard Mercator, a degree, whether of latitude or longitude, had been represented in all cases by the same length, and the course to be pursued by a vessel was marked on the map by a straight line joining the ports of arrival and departure. Mercator had seen that this led to considerable errors, and had realized that to make this method of tracing the course of a ship at all accurate, the space assigned on the map to a degree of latitude ought to gradually increase as the latitude increased. Using this principle, he had empirically constructed some charts which were published about 1560 or 1570. Wright set himself the problem to determine the theory on which such maps should be drawn, and succeeded in discovering the law of the scale of the maps, though his rule is strictly correct for small arcs only. The result was published in the second edition of Blundeville's Exercises. In 1599 Wright published his Certain Errors in Navigation Detected and Corrected, in which he explained the theory and inserted a table of meridional parts. The reasoning shews considerable geometrical power. In the course of the work he gives the declinations of 32 stars, explains the phenomenon of the dip, parallax, and refraction, and adds a table of magnetic declinations, but he assumes the Earth to be stationary. In the following year he published some maps constructed on his principle. In these the northernmost point of Australia is shewn, the latitude of London is taken to be 51 degrees 32 minutes. Snell. A contemporary of Guldinus and Wright was Wilbrod Snell, whose name is still well known through his discovery in 1619 of the law of refraction in optics. Snell was born at Leyden in 1591 and occupied a chair of mathematics at the university there, and died there on October 30th, 1626. He was one of those infant prodigies who occasionally appear. At the age of 12 he was acquainted with the standard mathematical works. I will here only add that in geodesy he laid down the true principles for measuring the arc of a meridian, and in spherical trigonometry he discovered the properties of the polar or supplemental triangle. Residual interest in pure geometry. The close of the 16th century was marked not only by the attempt to find a theory of dynamics based on laws derived from experiment, but also by a revived interest in geometry. This was largely due to the influence of Kepler. Johann Kepler, one of the founders of modern astronomy, was born of humble parents near Stuttgart on December 27, 1571, and died at Ratisbon on November 15, 1630. He was educated under Maestlin at Tübingen. In 1593 he was appointed professor at Graz, where he made the acquaintance of a wealthy and beautiful widow whom he married, but found too late that he had purchased his freedom from pecuniary troubles at the expense of domestic happiness. In 1599 he accepted an appointment as assistant to Tycho Brahe, and in 1601 succeeded his master as astronomer to the Emperor Rudolf II. But his career was dogged by bad luck. First his stipend wasn't paid, next his wife went mad and then died, and though he married again in 1611 this proved even more unfortunate venture than before, for though to secure a better choice he took the precaution to make a preliminary selection of 11 girls whose merits and demerits he carefully analyzed in a paper which is still extant, he finally selected the wrong one, while to complete his discomfort he was expelled from his chair and narrowly escaped condemnation for heterodoxy. During this time he depended for his income on telling fortunes and casting horoscopes, for, as he says, nature, which has conferred upon every animal the means of existence, has designed astrology as an adjunct and ally to astronomy. He seems however to have no scruple in charging heavily for his services, and to the surprise of his contemporaries was found at his death to have a considerable hoard of money. He died while on a journey to try and recover for the benefit of his children some of the arrears of his stipend. In describing Galileo's work I alluded briefly to the three laws in astronomy that Kepler had discovered, and in connection with which his name will be always associated, and I have already mentioned the prominent part he took in bringing logarithms into general use on the continent. These are familiar facts, but it is not known so generally that Kepler was also a geometrician and algebraist of considerable power, and that he, Desargues, and perhaps Galileo may be considered as forming a connecting link between the mathematicians of the Renaissance and those of modern times. Kepler's work in geometry consists rather in certain general principles which he laid down and illustrated by a few cases than in any systematic exposition of the subject. In a short chapter on conics inserted in his Parallelopomena, published in 1604, he lays down what has been called the principle of continuity, and gives an example of the statement that a parabola is at once the limiting case of an ellipse and of a hyperbola. He illustrates the same doctrine by reference to the foci of conics. The word focus was introduced by him, and he also explains that the parallel lines should be regarded as meeting at infinity. In his Stereometrica, which was published in 1615, he determines the volume of certain vessels and the areas of certain surfaces by means of infinitesimals instead of by the long and tedious method of exhaustions. These investigations, as well as those of 1604, arose from a dispute with a wine merchant as to the proper way of gauging the contents of a cask. This use of infinitesimals was objected to by Guldinus and other writers as inaccurate, but though the methods of Kepler are not altogether free from objection, he was substantially correct, and by applying the law of continuity to infinitesimals he prepared the way for Cavalieri's method of indivisibles and the infinitesimal calculus of Newton and Leibniz. Kepler's work on astronomy lies outside the scope of this book. I will mention only that it was founded on the observations of Tycho Brahe, whose assistant he was. His three laws of planetary motion were the result of many and laborious efforts to reduce the phenomenon of the solar system to certain simple rules. The first two were published in 1609 and stated that the planets describe ellipses around the sun being a focus, and that the line joining the sun to any planet sweeps over equal areas in equal times. The third was published in 1619 and stated that the square of the periodic times of the planets are proportional to the cubes of the major axes of their orbits. I thought to add that he attempted to explain why these motions took place by a hypothesis which is not very different from Descartes' theory of vortices. Kepler also devoted considerable time to the elucidation of theories of visions and refractions in optics. While the conception of the geometry of the Greeks were being extended by Kepler, a Frenchman, whose name until recently was almost unknown, was inventing a new method of investigating the subject, a method which is now known as projective geometry. This was the discovery of Desargues, whom I put with some hesitation at the close of this period and not among the mathematicians of modern times. Desargues. Gerard Desargues, born at Lyon in 1593 and died in 1662, was by profession an engineer and architect, but gave some courses of gratuitous lectures in Paris from 1626 to about 1630, which made a great impression upon his contemporaries. Both Descartes and Pascal had a high opinion of his work and abilities, and both made considerable use of the theorems he had enunciated. In 1636 Desargues issued a work on perspective, but most of his researches were embodied in his Brillant Project on conics, published in 1639, a copy of which was discovered by Charles in 1845. I take the following summary of it from Charles Taylor's work on conics. Desargues commences with the statement of the doctrine of continuity as laid down by Kepler. Thus the points at the opposite ends of a straight line are regarded as coincident. Parallel lines are treated as meeting at a point at infinity, and parallel planes on a line at infinity, while a straight line may be considered as a circle whose centre is at infinity. The theory of involution of 6 points with its special cases is laid down, and the projective property of pencils in involution is established. The theory of polar lines is expounded, and its analogue in space suggested. A tangent is defined as the limiting case of a secant, and an asymptote as a tangent at infinity. Desargues shews that the lines which join 4 points in a plane determine 3 pairs of lines in involution on any transversal, and from any conic through the 4 points another pair of lines can be obtained which are in involution with any 2 of the former. He proves that the points of intersection of the diagonals and the 2 pairs of opposite sides of any quadrilateral inscribed in a conic are a conjugate triad with respect to the conic, and when one of the 3 points is infinity its polar is a diameter. But he fails to explain the case in which the quadrilateral is a parallelogram, although he had formed the conception of a straight line which was wholly at infinity. The book therefore may be fairly said to contain the fundamental theorems on involution, homology, poles and polars, and perspective. The influence exerted by the lectures of Desargues on Descartes, Pascal, and the French geometricians of the 17th century was considerable, but the subject of projective geometry soon fell into oblivion, chiefly because the analytical geometry of Descartes was so much more powerful as a method of proof or discovery. The researches of Kepler and Desargues will serve to remind us that the geometry of the Greeks was not capable of much further extension. Mathematicians were now beginning to seek new methods of investigation, and were extending the conceptions of geometry. The invention of analytical geometry and of the infinitesimal calculus temporarily diverted attention from pure geometry. But at the beginning of the present century there was a revival of interest in it, and since then it has been a favourite subject of study with many mathematicians. Mathematical knowledge at the close of the Renaissance. Thus by the beginning of the 17th century we may say that the fundamental principles of arithmetic, algebra, theory of equations, and trigonometry had been laid down, and the outlines of the subject as we know them have been traced. It must be however remembered that there were no good elementary textbooks on these subjects, and a knowledge of them was therefore confined to those who could extract it from the ponderous treatises in which it lay buried. Though much of the modern algebraical and trigonometrical notation had been introduced, it was not familiar to mathematicians, nor was it even universally accepted, and it was not until the end of the 17th century that the language of these subjects was definitely fixed. Considering the absence of good textbooks, I am inclined rather to admire the rapidity with which it came into universal use, than to cavil at the hesitation to trust it alone which many writers shewed. If we turn to applied mathematics, we find on the other hand that the science of statics had made but little advance in the 18 centuries that had elapsed since the time of Archimedes, while the foundations of dynamics were laid by Galileo only at the close of the 16th century. In fact, as we shall see later, it was not until the time of Newton that the science of mechanics was placed on a satisfactory basis. The fundamental conceptions of mechanics are difficult, but the ignorance of the principles of the subject shewn by mathematicians of this time is greater than would have been anticipated from their knowledge of pure mathematics. With this exception we may say that the principles of analytical geometry and of the infinitesimal calculus were needed before there was likely to be much further progress. The former was employed by Descartes in 1637, the latter invented by Newton and possibly independently by Leibniz some 30 or 40 years later, and their introduction may be taken as marking the commencement of the period of modern mathematics. End of section 19. Chapter 14. Features of modern mathematics. The division between this period and that treated in the last 6 chapters is by no means so well defined as that which separates the history of Greek mathematics from the mathematics of the Middle Ages. The methods of analysis used in the 17th century and the kind of problems attacked changed but gradually, and the mathematicians at the beginning of this period were in immediate relations with those at the end of the last considered. For this reason some writers have divided the history of mathematics into 2 parts only, treating the schoolmen as the lineal successors of the Greek mathematicians, and dating the creation of modern mathematics from the introduction of the Arab textbooks into Europe. The division I have given is, I think, more convenient, for the introduction of analytical geometry and of the calculus completely revolutionized the development of the subject, and it therefore seems preferable to take their invention as marking the commencement of modern mathematics. The time that has elapsed since these methods were invented has been a period of incessant intellectual activity in all departments of knowledge, and the progress made in mathematics has been immense. The greatly extended range of knowledge and the rapid intercommunication of ideas due to printing increase the difficulties of a historian, while the mass of materials which has to be mastered, the absence of perspective, and even the echoes of old controversies combine to make it very difficult to give a clear and just account of the development of the subject. As, however, the leading facts are generally known, and the works published during this time are accessible to any student, I may deal more concisely with the lives and writings of modern mathematicians than with those of their predecessors, and confine myself more strictly than before to those who have materially affected the progress of the subject. Roughly speaking, we may say that 5 distinct stages in the history of this period can be discerned. First of all, there is the invention of analytical geometry by Descartes in 1637, and almost at the same time the introduction of the method of indivisibles, by the use of which areas, volumes, and the positions of centres of mass can be determined by summation in a manner analogous to that effected nowadays by the aid of the integral calculus. The method of indivisibles was soon superseded by the integral calculus. Analytical geometry, however, maintains its position as part of the necessary training of every mathematician, and is incomparably more potent than the geometry of the ancients for all purposes of research. The latter is still no doubt an admirable intellectual training, and it frequently affords an elegant demonstration of some proposition the truth of which is already known, but it requires a special procedure for every particular problem attacked. The former, on the other hand, lays down a few simple rules by which property can be at once proved or disproved. In the second place, we have the invention of the fluxional or differential calculus about 1666, and possibly an independent invention of it in 1674. Wherever a quantity changes according to some continuous law, and most things in nature do so change, the differential calculus enables us to measure its rate of increase or decrease. And from its rate of increase or decrease, the integral calculus enables us to find the original quantity. Formerly, every separate function of x, such as 1 plus x quantity to the power n, or the logarithm of 1 plus x, the sine of x, or the arctan of x, etc., could be expanded in ascending powers of x only by means of such special procedure as was suitable for that particular problem. But by the aid of the calculus, the expansion of any function of x in ascending powers of x is in general reducible to one rule which covers all cases alike. So again the theory of maxima and minima, the determination of the lengths of curves and the areas enclosed by them, the determination of surfaces of volumes and the centres of mass, and many other problems are each reducible to a single rule. The theories of differential equations, of the calculus of variations, of finite differences, etc., are the developments of the ideas of the calculus. These two subjects, analytical geometry and the calculus, became the chief instruments of further progress in mathematics. In both of them, a sort of machine was constructed to solve a problem. It was only necessary to put in the particular function dealt with, or the equation of the particular curve or surface considered, and on performing certain simple operations the result came out. The validity of the process was proved once and for all, and it was no longer requisite to invent some special method for every separate function, curve, or surface. In the third place, Huygens laid the foundation of a satisfactory treatment of dynamics, and Newton reduced it to an exact science. The latter mathematician proceeded to apply the new analytical methods not only to numerous problems in the mechanics of solids and fluids on the earth, but to the solar system. The whole of mechanics, terrestrial and celestial, was thus brought within the domain of mathematics. There is no doubt that Newton used the calculus to obtain many of his results, but he seems to have thought that, if his demonstrations were established by the aid of a new science which was at that time generally unknown, his critics, who would not understand the fluxional calculus, would fail to realize the truth and importance of his discoveries. He therefore determined to give geometrical proofs of all of his results. He accordingly cast the Principia into a geometrical form, and thus presented it to the world in a language which all men could then understand. The theory of mechanics was extended and was systematized into its modern form by Laplace and Lagrange toward the end of the 18th century. In the fourth place, we may say that during this period the chief branches of physics have been brought within the scope of mathematics. This extension of the domain of mathematics was commenced by Huygens and Newton when they propounded their theories of light, but it was not until the beginning of this century that sufficiently accurate observations were made in the most physical subjects to enable mathematical reasoning to be applied to them. From the results of the observations and experiments which have been since published, numerous and far-reaching conclusions have been obtained by the use of mathematics, but we now want some more simple hypotheses from which we can deduce those laws which at present form our starting point. If, to take one example, we could say in what electricity consisted, we might get some simple laws or hypotheses from which by the aid of mathematics all the observed phenomenon could be then deduced, in the same way as Newton deduced all the results of physical astronomy from the law of gravitation. All lines of research seem moreover to indicate that there is an intimate connection between the different branches of physics, e.g. between light, heat, electricity, and magnetism. The ultimate explanation of this and of the leading facts in physics seems to demand a study of molecular physics. A knowledge of molecular physics in its turn seems to require some theory as to the constitution of matter. It would further appear that the key to the constitution of matter is to be found in chemistry or chemical physics. So the matter stands at present. Helmholtz in Germany and Maxwell and Lord Kelvin (Sir William Thomson) in Great Britain have done a great deal in applying mathematics to physics, but the connection between the different branches of physics and the fundamental laws of those branches, if there be any simple ones, are riddles which are not yet solved. This history does not pretend to treat of problems which are now the subject of investigation, and though mathematical physics forms a large part of modern mathematics, I shall not discuss it in any detail. Fifthly, this period has seen an immense extension of pure mathematics. Much of this is the creation of comparatively recent times, and I regard the details of it as outside the limits of this book, though in chapter 19 I have allowed myself to mention some of the subjects discussed. The most striking features of this extension are the developments of higher geometry, of higher arithmetic, or the theory of numbers, of higher algebra, including the theory of forms, and of the theory of equations, and also the discussion of functions of double and multiple periodicity, and notably the creation of a theory of functions. End of section 20. Chapter 15. History of mathematics from Descartes to Huygens, circa 1635 to 1675. I propose in this chapter to consider the history of mathematics during the 40 years in the middle of the 17th century. I regard Descartes, Cavalieri, Pascal, Wallis, Fermat, and Huygens as the leading mathematicians of this time. I shall treat them in that order, and I shall conclude with a brief list of the more eminent remaining mathematicians of the same date. I have already stated that the mathematicians of this period, and the remark applies more particularly to Descartes, Pascal, and Fermat, were largely influenced by the teaching of Kepler and Desargues, and I would repeat again that I regard these latter and Galileo as forming a connecting link between the writers of the Renaissance and those of modern times. I should also add that the mathematicians considered in this chapter were contemporaries, and although I have tried to place them roughly in such an order that their chief works shall come in chronological arrangement, it is essential to remember that they were in relation with one another, and in general were acquainted with one another's researches as soon as they were published. Descartes. Subject to the above remarks, we may consider Descartes as the first of the modern school of mathematics. René Descartes was born near Tours on March 31, 1596, and died at Stockholm on February 11, 1650. He was thus a contemporary of Galileo and Desargues. His father, who as the name implies was of a good family, was accustomed to spend half the year at Rennes when the local parliament in which he held a commission as a councillor was in session, and the rest of the time on his family estate at Les Cartes at La Haye. René, the second of a family of 2 sons and 1 daughter, was sent at the age of 8 years to the Jesuit school at La Flèche, and of the admirable discipline and education there given he speaks most highly. On account of his delicate health he was permitted to lie in bed till late in the morning. This was a custom which he had always followed, and when he visited Pascal in 1647 he told him that the only way to do good work in mathematics and to preserve his health was never to allow anyone to make him get up in the morning before he felt inclined to do so, an opinion which I chronicle for the benefit of any schoolboy into whose hands this work may fall. On leaving school in 1612, Descartes went to Paris to be introduced to the world of fashion. Here, through the medium of the Jesuits, he made the acquaintance of Midorge, and renewed his schoolboy friendship with Father Mersenne, and together with them he devoted the 2 years of 1615 and 1616 to the study of mathematics. At the time a man of position usually entered either the army or the church. Descartes chose the former profession, and in 1617 joined the army of Prince Maurice of Orange, then at Breda. Walking through the streets he saw a placard in Dutch which excited his curiosity, and stopping the first passer asked him to translate it into either French or Latin. The stranger, who happened to be Isaac Beeckman, the head of the Dutch college at Dort, offered to do so if Descartes would answer it, the placard being in fact a challenge to all the world to solve a geometrical problem there given. Descartes worked it out within a few hours, and a warm friendship between him and Beeckman was the result. This unexpected test of his mathematical attainments made the uncongenial life of the army distasteful to him, but under family influence and tradition he remained a soldier, and was persuaded at the commencement of the 30 Years' War to volunteer under the court at Bucquoy in the army of Bavaria. He continued all this time to occupy his leisure with mathematical studies, and was accustomed to date the first ideas of his new philosophy and of his analytical geometry from 3 dreams he experienced on the night of November 10, 1619 at Neuburg, when campaigning on the Danube. He regarded this as the critical day of his life, and one which determined his whole future. He resigned his commission in the spring of 1621, and spent the next 5 years in travel, during most of which time he continued to study pure mathematics. In 1626 we find him settled at Paris, a little well-built figure, modestly clad in green taffety, and only wearing a sword and feather in token of his quality as a gentleman. During the first 2 years there he interested himself in general society, and spent his leisure in the construction of optical instruments, but these pursuits were merely the relaxations of one who failed to find in philosophy that theory of the universe which he was convinced finally awaited him. In 1628 Cardinal de Bray, the founder of the Oratorians, met Descartes, and was so much impressed by his conversation that he urged on him the duty of devoting his life to the examination of truth. Descartes agreed, and the better to secure himself from interruption moved to Holland, then at the height of its power. There for 20 years he lived, giving up all his time to philosophy and mathematics. Science, he says, may be compared to a tree. Metaphysics is the root, physics is the trunk, and the three chief branches are mechanics, medicine, and morals, these forming the three applications of our knowledge, namely to the external world, to the human body, and to the conduct of life, and with these subjects alone his writings are concerned. He spent the first 4 years, 1629 to 1633, of his stay in Holland in writing Le Monde, which embodies an attempt to give a physical theory of the universe, but finding that its publication was likely to bring on him the hostility of the church, and having no desire to pose as a martyr, he abandoned it. The complete manuscript was published in 1664. He then devoted himself to composing a treatise on universal science. This was published at Leyden in 1637, titled The Discourse on Method, and was accompanied with three appendices entitled Optics, Meteorology, and Geometry. It is from the last of these that the invention of analytical geometry dates. In 1641 he published a work called Meditations, in which he explained at some length his views of philosophy as sketched out in the Discourse. In 1644 he issued the Principia Philosophiae, as a greater part of which was devoted to physical science, especially the laws of motion and the theory of vortices. In 1647 he received a pension from the French court in honour of his discoveries. He went to Sweden on the invitation of the Queen in 1649, and died a few months later of inflammation of the lungs. In appearance Descartes was a small man with a large head, projecting brow, prominent nose, and black hair coming down to his eyebrows. His voice was feeble. Considering the range of his studies he was by no means widely read, and he despised both learning and art unless something tangible could be extracted therefrom. In disposition he was cold and selfish. He never married and left no descendants, though he had one illegitimate daughter who died young. As to his philosophical theories, it would be sufficient to say that he discussed the same problems which have been debated for the last 2000 years. It is hardly necessary to say that the problems themselves are of great interest, but from the nature of the case no solution ever offered is capable either of proof or disproof, and whenever a philosopher like Descartes believes that he has at last finally settled a question, it has been easy for his successors to point out the fallacy in his assumptions. All that can be effected is to make one explanation somewhat more probable than another. I have read somewhere that philosophy has always been chiefly engaged with the interrelations of God, nature, and man. The earliest philosophers were Greeks, who occupied themselves mainly with the relations between God and nature, and dealt with man separately. The Christian Church was so absorbed in the relation of God to man as to entirely neglect nature. Finally, modern philosophers concern themselves chiefly with the relations between man and nature. Whether this is a correct historical generalization of the views which have been successfully prevalent, I do not care to discuss here, but the statement as to the scope of modern philosophy marks the limitations of Descartes' writings, and they may be taken as the commencement of the modern school. Descartes' chief contributions to mathematics were his analytical geometry and his theory of vortices, and it is on his researches in connection with the former of these subjects that his reputation rests. Analytical geometry does not consist merely, as sometimes is loosely said, in the application of algebra to geometry. That had been done by Archimedes and many others, and had become the usual method of procedure in the works of the mathematicians of the 16th century. The great advance made by Descartes was that he saw that a point in a plane could be completely determined if its distances, say x and y, formed two fixed lines drawn at right angles in the plane, were given, with the convention familiar to us as to the interpretation of positive and negative values. and that though an equation f of xy equals 0 was indeterminate and could be satisfied by an infinite number of values of x and y, yet these values of x and y determine the coordinates of a number of points which form a curve of which the equation f of xy equals 0 expresses some geometrical property, that is, a property true of the curve at every point on it. Descartes assured that a point in space could be similarly determined by three coordinates, but he confined his attention to plane curves. It was at once seen by Descartes and his successors that in order to investigate the properties of a curve it was sufficient to select any characteristic geometrical property as a definition, and to express it by means of an equation between the current coordinates of any point on the curve, that is, to translate the definition into a language of analytical geometry. The equation so obtained contains implicitly every property of the curve, and any particular property can be deduced from it by ordinary algebra without troubling about the geometry of the figure. The points in which the two curves intersect can be determined by finding the roots common to their two equations. I need not go further into details, for nearly everyone to whom the above is intelligible will have read analytical geometry and be able to appreciate the value of its invention. Descartes' Geometrie is divided into three books. The first two of these treat of analytical geometry, and the third includes an analysis of the algebra then current. It is somewhat difficult to follow the reasoning, but the obscurity was intentional and due to the jealousy of Descartes.
Translated, I omitted nothing, says he, except design. I had expected that people who have any math skill would not fail to say that I had not said anything that has not already been said about the coordinate system, but I have hopefully made this topic more intelligible. The first book commences with an explanation of the principles of analytic geometry, and contains a discussion of a certain problem which has been propounded by Pappus in the seventh book of his Synagogue, and of which some particular cases have been considered by Euclid and Apollonius. The general theorem has baffled previous geometricians, and it was in the attempt to solve it that Descartes was led to the invention of analytical geometry. The full enunciation of the problem is rather involved, but the most important case is to find the locus of a point such that the product of the perpendiculars on M given straight lines shall be in a constant ratio to the product of the perpendiculars on N given straight lines. The ancients had solved this geometrically for the case m equals 1, n equals 1, and the case m equals 1, n equals 2. Pappus had further stated that if m equals n equals 2, the locus was a conic, but he gave no proof. Descartes also failed to prove this by pure geometry, but he shewed that the curve was represented by an equation of the second degree, that is, it was a conic section. Subsequently, Newton gave an elegant solution of the problem by pure geometry. In the second book, Descartes divides curves into two classes, namely geometrical and mechanical curves. He defines geometrical curves as those which can be generated by the intersection of two lines each moving parallel to one coordinate axis, with commensurable velocities, by which he meant that dy by dx was an algebraical function, as for example is the case in the ellipse and the cissoid. He calls the curve mechanical when the ratio of the velocities of these lines is incommensurable, by which he meant that dy by dx was a transcendental function, as for example is the case in the cycloid and the quadratrix. Descartes confined his discussion to algebraical curves, and did not treat of the theory of mechanical curves. The classification into algebraical and transcendental curves now usual is due to Newton. Descartes also paid particular attention to the theory of the tangents to curves, as perhaps might be inferred from his system of classification just alluded to. Then the current definition of a tangent at a point was a straight line through the point such that, between it and the curve, no other straight line could be drawn, i.e. the straight line of closest contact. Descartes proposed to substitute for this that the tangent was the limiting position of the secant. Fermat, and at a later date Maclaurin and Lagrange, adopted this definition. Barrow, followed by Newton and Leibniz, considered the curve as the limit of an inscribed polygon when the sides become indefinitely small, and stated that the side of the polygon when produced became in the limit a tangent to the curve. Roberval, on the other hand, defined a tangent at a point as the direction of the motion at that instant of a point which was describing the curve. The results are the same whichever definition is selected, but the controversy as to which definition was the correct one was none the less lively. Descartes illustrated his theory by giving the general rule for drawing tangents and normals to a roulette. The method used by Descartes for finding the tangent or normal at any point of a given curve was substantially as follows. He determined the centre and radius of a circle which should cut the curve in two consecutive points there. The tangent to the circle at that point will be the required tangent to the curve. In modern textbooks it is usual to express the condition that two of the points in which a straight line, such as y equals mx plus c, cuts the curve shall coincide with the given point. This enables us to determine m and c, and thus the equation of the tangent there is determined. Descartes, however, did not venture to do this, but selecting a circle as the simplest curve, and one to which we know how to draw a tangent, he so fixed his circle as to make it touch the given curve at the point in question, and thus reduce the problem to drawing a tangent to a circle. I should note in passing that he only applied this method to curves which are symmetrical about an axis, and he took the centre of the circle on the axis. Much of the reasoning in these two books is not easy to follow, but a Latin translation of them with explanatory notes was prepared by F. de Boon, and an edition of this with commentary by F. van Schooten was issued in 1659 and had a wide circulation. The third book of Geometrie contains an analysis of the algebra then current, and it has affected the language of the subject by fixing the custom of employing the letters at the beginning of the alphabet to denote known quantities, and those at the end of the alphabet to denote unknown quantities. Descartes further introduced the system of indices now in use, but I would here remind the reader that the suggestion had been made by previous writers, though it had not been generally adopted, but very likely it was the original on the part of Descartes. I think also that Descartes was the first to realize that his letters might represent any quantities, positive or negative, and that it was sufficient to prove a proposition for one general case compared to the old procedure. In this book he made use of the rule for determining a limit to the number of positive and negative roots of an algebraical equation, which is still known by his name, and introduced the method of indeterminate coefficients for the solution of equations. He believed that he had given a method by which algebraical equations of any order could be solved, but in this he was mistaken. He made use of the method of indeterminate coefficients. Of the other two appendices to the discourse was one devoted to optics. The chief interest of this consists in the statement given of the law of refraction. This appears to have been taken from Snell's work. But not only is there no acknowledgment of the source from which it was obtained, but it is enunciated in such a way so as to lead a careless reader to suppose that it is due to the researches of Descartes. Descartes would seem to have repeated Snell's experiments when in Paris in 1626 or 1627, and it is possible that he subsequently forgot how much he owed to the earlier investigations of Snell. A large part of the optics is devoted to determining the best shape for the lenses of a telescope, but the mechanical difficulties in grinding a surface of glass to a required form are so great as to render these investigations of little practical use. Descartes seems to have been doubtful whether to regard the rays of light as proceeding from the eye and so to speak touching the object, as the Greeks had done, or as proceeding from the object and so affecting the eye; but, since he considered the velocity of light to be infinite, he did not deem the point particularly important. The other appendix on meteors contains an explanation of numerous atmospheric phenomena, including the rainbow. Descartes was unacquainted with the unequal refrangibility of rays of light of different colours, and the explanation of the latter is necessarily incomplete. Descartes' physical theory of the universe, embodying most of the results contained in his earlier and unpublished Le Monde, was given in his Principia 1644 and rests on a metaphysical basis. He commences with a discussion on motion and then lays down 10 laws of nature, of which the first 2 are almost identical with the first 2 laws of motion as given by Newton. The remaining 8 laws are inaccurate. He next proceeds to discuss the nature of matter, which he regards as uniform in kind, though there are 3 forms of it. He assumes that the matter of the universe must be in motion, and that the motion must result in a number of vortices. He states that the sun is the centre of an immense whirlpool of this matter, in which the planets float and are swept round like straws in a whirlpool of water. Each planet is supposed to be the centre of a secondary whirlpool by which its satellites are carried. These secondary whirlpools are supposed to produce variations of density in the surrounding medium, which constitute the primary whirlpool, and so cause the planets to move on in ellipses and not circles. All these assumptions are arbitrary and unsupported by any investigation. It is not difficult to prove that on his hypothesis the sun would be in the centre of these ellipses and not at a focus, as Kepler had shewn was the case, and that the weight of a body at every place on the surface of the earth except the equator would act in a direction which was not vertical. But it will be sufficient here to say that Newton, in the second book of his Principia in 1687, considered the theory in detail and shewed that its consequences are not only inconsistent with each of Kepler's laws and with the fundamental laws of mechanics, but are also at variance with the 10 laws of nature assumed by Descartes. Still, in spite of its crudeness and its inherent defects, the theory of vortices marks a fresh era in astronomy, for it was an attempt to explain the phenomenon of the whole universe by the same mechanical laws which experiments shews to be true here on earth. Cavalieri. Almost contemporaneously with the publication in 1637 of Descartes' geometry, the principles of the integral calculus, so far as they are concerned with summation, were being worked out in Italy. This was effected by what was called the principle of indivisibles, and was the invention of Cavalieri. It was applied to numerous problems connected with the quadrature of curves and surfaces, the determination of volumes, and the positions of centres of mass, to the complete exclusion of the tedious method of exhaustions used by the Greeks. In principle the methods are the same, but the notation of indivisibles is more concise and convenient. It was in its turn superseded at the beginning of the 18th century by the integral calculus, but its use will be familiar to all mathematicians who have read any commentary on the first section of the first book of Newton's Principia, in the application of lemmas 2 and 3 to the determination of areas, volumes, and so on. Bonaventura Cavalieri was born at Milan in 1598 and died at Bologna in November 27, 1647. He became a Jesuit at an early age, and on the recommendation of the order he was in 1629 made professor of mathematics at Bologna, and he continued to occupy the chair there until his death. I have already mentioned Cavalieri's name for the part of the book that he took in introducing the use of logarithms into Italy. He was one of the most influential mathematicians of his time, but his subsequent reputation rests mainly on his invention of the principle of indivisibles. The principle of indivisibles has been used by Kepler, in 1604 and 1615 in somewhat crude form. It was first stated by Cavalieri in 1629, but he did not publish his results till 1635. In his early enunciation of the principle in 1635, Cavalieri asserted that a line was made up of an infinite number of points, each without magnitude, and a surface of an infinite number of lines, each without breadth, and a volume of infinite number of surfaces, each without thickness. To meet the objections of Guldinus and others, the statement was recast, and in its final form used by the mathematicians of the 17th century. It was published in Cavalieri's Six Geometrical Exercises in 1647, the third of which is devoted to a defence of the theory. These exercises contain the first rigid demonstration of the properties of Pappus. Cavalieri's work on the subject were reissued with his later corrections in 1653. The method of indivisibles is simply that any magnitude may be divided into an infinite number of small quantities which can be made to bear any required ratios, for example equality, one to the other. The analysis given by Cavalieri is hardly worth quoting except as being one of the first steps taken toward the formation of an infinitesimal calculus. One example will suffice. Suppose it be required to find the area of a right-angled triangle. Let the base contain n points and the other side n times a points. Then the ordinates at the successive points of the base will contain a, 2a, and so on to n times a points. Therefore the number of points in the figure is a plus 2a plus ... plus na, the sum of which is half n squared a plus 1/2 n times a. Since n is very large, we may neglect the 1/2 na as inconsiderable compared with the 1/2 n squared a, and the area is 1/2 na times n, that is 1/2 the altitude times the base. There is no difficulty in criticizing such a proof, but although the form in which it is presented is indefensible, the substance of it is correct. It would be misleading to give the above as the only specimen of the method of indivisibles, and I therefore quote another example taken from a later writer, which will fairly illustrate the use of the method when modified and corrected by the method of limits. Let it be required to find the area bounded by the parabola APC, the tangent at A, and any diameter DC. Complete the parallelogram ABCD. Divide AD into n equal parts. Let AM contain r of them, and Mn be the r plus 1th part. Draw MP and NQ parallel to AB, and draw PR parallel to AD. Then, when n becomes indefinitely large, the curvilinear area APCD will be the limit of the sum of all parallelograms like Pn. Now the ratio of the area Pn to the area BD equals the ratio MP times Mn is to DC times AD. But by properties of the parabola, MP over DC equals AM squared over AD squared, which is also equal to r squared over n squared, and Mn over AD equals 1 over n. Hence MP times Mn over DC times AD equals r squared over n cubed. Therefore the area of Pn over the area of BD equals r squared over n cubed. Therefore ultimately the area of APCD over area BD equals 1 squared plus 2 squared plus 3 squared plus ... plus n minus 1 squared all over n cubed, which is also equal to 1/6 of n times n minus 1 times 2n minus 1 all over n cubed, which in the limit 1 to 3. It is perhaps worth noticing that Cavalieri and his successors always used the method to find the ratios of two areas, volumes, or magnitudes of the same kind and dimensions. That is, they never thought of an area as containing so many units of area. The idea of comparing a magnitude with a unit of the same kind seems to have been due to Wallis.
It is evident that in its direct form the method is applicable to only a few curves. Cavalieri proved that if m be a positive integer, then the limit, when n is infinite, of 1 to the m plus 2 to the m plus 3 to the m plus n to the m all over n to the m plus 1 is 1 over m plus 1, which is equivalent to saying that he found the integral to x of x to the m from x equals 0 to x equals 1. He also discussed the quadrature of the hyperbola. End of chapter 21, part 1. Pascal. Among the contemporaries of Descartes, none displayed greater natural genius than Pascal, but his reputation rests more on what he might have done than on what he actually effected, as during a considerable part of his life he deemed it his duty to devote his whole time to religious exercises. Blaise Pascal was born at Clermont on June 19, 1623, and died at Paris on August 19, 1662. His father, a local judge at Clermont and himself of some scientific reputation, moved to Paris in 1631, partly to prosecute his own scientific studies, partly to carry on the education of his only son who had already displayed exceptional ability. Pascal was kept at home in order to assure his not being overworked, and with the same object it was directed that his education should be at first confined to the study of languages and should not include any mathematics. This naturally excited the boy's curiosity, and one day, being then 12 years old, he asked in what geometry consisted. His tutor replied that it was the science of constructing exact figures and of determining the proportions between their different parts. Pascal, stimulated no doubt by the injunction against reading it, gave up his playtime to the new study, and in a few weeks had discovered for himself many properties of figures, and in particular the proposition that the sum of the angles of a triangle is equal to 2 right angles. I have read somewhere, but I cannot lay my hand on the authority, that his proof merely consisted in turning the angular points of a triangular piece of paper over so as to meet in the centre of the inscribed circle. A similar demonstration can be got by turning the angular points over so as to meet at the foot of the perpendicular drawn from the biggest angle to the opposite side. His father, struck by this display of ability, gave him a copy of Euclid's Elements, a book which Pascal read with avidity and soon mastered. At the age of 14 he was admitted to the weekly meetings of Roberval, Mersenne, Midorge, and other French geometricians, from which the French Academy ultimately sprung, being created by ordinance of Louis XIV on December 22, 1666. At 16 Pascal wrote an essay on conic sections, and in 1641, at the age of 18, he constructed the first arithmetical machine, an instrument which 8 years later he further improved and patented. His correspondence with Fermat about this time shews that he was then turning his attention to analytical geometry and physics. He repeated Torricelli's experiments by which the pressure of the atmosphere could be estimated as a weight, and he confirmed his theory of the cause of barometrical variations by obtaining at the same instant readings at different altitudes on the hill of Puy de Dôme. In 1650, when in the midst of these researches, Pascal suddenly abandoned his favourite pursuits to study religion, or, as he says in his Pensées, to contemplate the greatness and the misery of man, and about the same time he persuaded the younger of his 2 sisters to enter the Port Royal Society. In 1653 he had to administer his father's estate. He now took up his old life again, and made several experiments on pressure exerted by gases and liquids. It was also about this period that he invented the arithmetical triangle, and together with Fermat created the calculus of probabilities. He was meditating marriage when an accident again turned the current of his thoughts to a religious life. He was driving a four in hand on November 23, 1654, when the horses ran away. The two leaders dashed over the parapet of the bridge at Neuilly, and Pascal was only saved by the traces breaking. Always somewhat of a mystic, he considered this a special summons to abandon the world. He wrote an account of the accident on a small piece of parchment, which for the rest of his life he wore next to his heart to perpetually remind him of his covenant, and shortly moved to Port Royal, where he continued to live until his death in 1662. Always delicate, he had injured his health by his incessant study. From the age of 17 or 18 he suffered from insomnia and acute dyspepsia, and at the time of his death was completely worn out. His famous provincial letters directed against the Jesuits and his Pensées were written towards the close of his life, and are the first example of that finished form which is characteristic of the best French literature. The only mathematical work that he produced after retiring to Port Royal was the essay of the cycloid in 1658. He was suffering from sleeplessness and a toothache when the idea occurred to him, and to his surprise his teeth immediately ceased to ache. Regarding this as a divine intimation to proceed with the problem, he worked incessantly for 8 days at it, and completed a tolerably full account of the geometry of the cycloid. I now proceed to consider his mathematical works in rather greater detail. His early essay of the geometry of conics, written in 1639 but not published until 1779, seems to have been founded on the teachings of Desargues. Two of the results are important as well as interesting. The first of these is the theorem known now as Pascal's theorem, namely that if a hexagon is inscribed in a conic, the points of the intersection of the opposite sides will lie in a straight line. The second, which is really due to Desargues, is that if a quadrilateral be inscribed in a conic, and a straight line be drawn cutting the sides taken in order in the points A, B, C, and D, and the conic in P and Q, then PA times PC over PD times PD equals QA times QC over QB times QD.
Pascal's arithmetical triangle, known today as Pascal's triangle, was written in 1653, but not printed until 1665. The triangle is constructed as in the annexed figure. By the way, the annexed figure shows Pascal's triangle as being kind of on its side by today's standards. A 1 at the apex followed by a 1, 1, and then in the third row 1, 2, 1, and in the fourth row 1, 3, 3, 1, and in the fifth row 1, 4, 6, 4, 1. So they will refer to these lines as diagonal lines. The horizontal lines, the way they're depicted, are 1, 1, 1, 1, 1, 1, 2, 3, 4, 5, 1, 3, 6, 10, 15, 1, 4, 10, 20, 35, and 1, 5, 15, 35, 70. And they have that written in actual rows and columns. So taking the latter description, each horizontal line being formed from the one above it by making every number in it equal to the sum of those above it and to the left of it in the row immediately above. For example, in the fourth line, 20 is equal to 1 plus 3 plus 6 plus 10. Then Pascal's arithmetical triangle to any required order is got by drawing a diagonal downwards from the right to left as in the figure. The numbers are what are now called the figurate numbers. Those in the first line are called the numbers of the first order. Those in the second line, 1, 2, 3, 4, 5, and so on, are called natural numbers or numbers of the second order. Those in the third line, numbers of the third order, and so on. It is easily shown that the mth number in the nth row is m plus n minus 2 factorial divided by m minus 1 factorial times n minus 1 factorial. The numbers in any diagonal give the coefficients of the expansion of a binomial. For example, the figures in the fifth diagonal, namely 1, 4, 6, 4, 1, are the coefficients in the expansion of a plus b raised to the power 4. Pascal used the triangle partly for this purpose, and partly to find the numbers of combinations of m things taken n at a time, which he stated correctly to be n plus 1 times n plus 2 times n plus 3 times m divided by m minus n factorial. Perhaps as a mathematician Pascal is best known in connection with his correspondence with Fermat in 1654, in which he laid down the principles of the theory of probabilities. This correspondence arose from a problem proposed by a gamester, the Chevalier de Mer, to Pascal, who communicated it to Fermat. The problem was this: two players of equal skill want to leave the table before finishing the game. Their scores and the number of points which constitute the game being given, it is desired to find in what proportion should they divide the stakes. Pascal and Fermat agreed on the answer but gave different proofs. The following is a translation of Pascal's solution. That of Fermat is given later. The following is my method for determining the share of each player when, for example, two players play a game of 3 points and each player has staked 32 pistoles. Suppose that the first player had gained 2 points and then the second player 1 point. They now have to play for a point on this condition, that if the first player gain, he takes all the money which is at stake, namely 64 pistoles, while if the second player gain, each player has 2 points, so that they are on terms of equality, and if they leave off playing, each ought to take 32 pistoles. Thus, if the first player gain, then 64 pistoles belong to him, and if he loses, then 32 pistoles belong to him. If therefore the players do not wish to play this game but to separate without playing it, the first player would say to the second, "I am certain of 32 pistoles even if I lose this game, and for the other 32 pistoles perhaps I shall have them and perhaps you will have them. The chances are equal. Let us divide these 32 pistoles equally and give me also the 32 pistoles of which I am certain." Thus the first player will have 48 pistoles and the second 16 pistoles. Next, suppose that the first player has gained 2 points and the second player none, and they are about to play for a point. The condition is that if the first player gain this point, he secures the game and takes 64 pistoles, and if the second player gain this point, then the players will be in the situation already examined, in which the first player is entitled to 48 pistoles and the second to 16 pistoles. Thus, if they do not wish to play, the first player would say to the second, "If I gain this point, I gain 64 pistoles. If I lose it, I am entitled to 48 pistoles. Give me then the 48 pistoles of which I am certain, and divide the other 16, since our chances of gaining the point are equal." Thus the first player will have 56 pistoles and the second player 8 pistoles. Finally, suppose that the first player had gained 1 point and the second player none. If they proceed to play for a point, the condition is that if the first player gain it, the players will be in the situation first examined, in which the first player is entitled to 56 pistoles. If the first player lose the point, each player has then a point and each is entitled to 32 pistoles. Give me the 32 pistoles of which I am certain, and divide the remainder of the 56 pistoles equally, that is, divide the 24 pistoles equally. Thus the first player will have the sum of 32 and 12 pistoles, that is 44 pistoles, and consequently the second will have 20 pistoles. Pascal proceeds next to consider the similar problem when the game is won by whomever first obtains m plus n points, and one player has m while the other has n points. The answer is obtained by using the arithmetical triangle, or Pascal's triangle. The general solution, in which the skill of the players is unequal, is given in many modern textbooks on algebra and agrees with Pascal's result, though of course the notation of the latter is different and less convenient. Pascal made a most illegitimate use of the new theory in the seventh chapter of his Pensées. He practically puts his argument that, as the value of eternal happiness must be infinite, then even if the probability of a religious life ensuring eternal happiness be very small, still the expectation, which is measured by the product of the two, must be of sufficient magnitude to make it worth while to be religious. The argument, if worth anything, would apply equally to any religion which has promised eternal happiness to those who accepted its doctrines. If any conclusion may be drawn from the statement, it is the undesirability of applying mathematics to questions of morality of which some of the data are necessarily outside the range of an exact science. It is only fair to add that no one had more contempt than Pascal for those who changed their opinions according to the prospect of material benefit, and this isolated passage is at variance with the spirit of his writings. The last mathematical work of Pascal was that on the cycloid of 1658. The cycloid is the curve traced out by the point on the circumference of a circular hoop which rolls along a straight line. Galileo in 1630 had been the first to call attention to this curve, and had suggested that the arches of bridges should be built in the form of it. It is a graceful curve, but the only bridge with a cycloidal arch of which I have heard is the one built by Essex in the grounds of Trinity College at Cambridge. 4 years later, in 1634, Roberval found the area of the cycloid. Descartes thought little of this solution and defied him to find its tangents, the same challenge also being sent to Fermat, who at once solved the problem. Several questions connected with the curve and with the surface and volume generated by its revolution about its axis, base, or the tangent at its vertex were then proposed by various mathematicians. These and some analogous questions, as well as the positions of the centres of mass of the solids there formed, were solved by Pascal in 1658, and the results were issued as a challenge to the world. Wallis succeeded in solving all the questions except those connected with the centre of mass. Pascal's own solutions were effected by the method of indivisibles, and are similar to those which a modern mathematician would give by the aid of the integral calculus. He obtained by summation what are equivalent to the following integrals: the integral of sine phi d phi, also the integral of sine squared phi d phi, and also the integral of phi times sine phi d phi, one limit being either 0 or half pi. He also investigated the geometry of the Archimedean spiral. These researches, according to D'Alembert, form a connecting link between the geometry of Archimedes and the infinitesimal calculus of Newton. Wallis. John Wallis was born at Ashford on November 22, 1616, and died at Oxford on October 28, 1703. When 15 years old he happened to see a book on arithmetic in the hands of his brother. Struck with curiosity at the odd signs and symbols in it, he borrowed the book, and in a fortnight mastered the subject. It was intended that he should be a doctor, and he was sent to Emmanuel College, Cambridge. While there he kept an act on the doctrine of the circulation of the blood. This is said to have been the first occasion in Europe on which this theory was publicly maintained in disputation. His interests, however, centred on mathematics. He was elected to a fellowship at Queen's College, Cambridge, and subsequently took orders, but on the whole adhered to the Puritan party, whom he rendered great assistance in deciphering the royalist despatches. He however joined the moderate Presbyterians in signing the remonstrance against the execution of Charles I, by which he incurred the lasting hostility of the Independents. In spite of their opposition, he was appointed in 1649 to the Savilian chair of geometry at Oxford, where he lived until his death on October 28, 1703. Besides his mathematical works he wrote on theology, logic, and philosophy, and was the first to devise a system for teaching deaf mutes. I confine myself to a few notes on his more important mathematical writings. They are notable partly for the introduction of the use of infinite series as an ordinary part of analysis, and partly for the fact that they revealed and explained to all students the principles of those new methods which distinguish modern from classical mathematics. The most important of Wallis's works was his Arithmetica Infinitorum, which was published in 1656. In this treatise the methods of analysis of Descartes and Cavalieri were systematized and greatly extended, but their logical exposition is open to criticism. It at once became the standard book on the subject and is constantly referred to by subsequent writers. It is prefaced by a short tract on conic sections which was subsequently expanded into a separate treatise. He commences by proving the law of indices, shews that x to the 0, x to the minus 1, x to the minus 2, and so on represent 1, 1 over x squared, and so on. That x to the power of 1/2 represents the square root of x. That x to the power of 2/3 represents the cube root of x squared, and that generally that x to the exponent minus n represents the reciprocal of x to the power n, and that x to the p over q represents the qth root of x to the p. Leaving the numerous algebraical applications of this discovery, he next proceeds to find by the method of indivisibles the area enclosed between the curve y equals x to the m, the axis of x, and any ordinate x equals h, and he proves that the ratio of this area is equal to that of the parallelogram on the same base and of the same altitude, and is equal to the ratio 1 over m plus 1. He apparently assumed that the same result would be true also for the curve y equals ax raised to the power m, where a is any constant and m is any number positive or negative. But he only discusses the case of which the parabola of m equals 2 and that of the hyperbola in which m equals minus 1. In the latter case his interpretation of the result is incorrect. He then shews that similar results might be written down for any curve of the form y equals the sum of ax raised to the power m, and hence that if the ordinate y on a curve can be expanded in powers of the abscissa x, its quadrature can be determined. Thus he said that if the equation of a curve were y equals x to the 0 plus x to the 1 plus x squared and so on, its area would be x plus 1/2 x squared plus 1/3 x cubed, and so on. He then applies this to the quadrature of the curves y equals quantity x minus x squared to the power 0, y equals the quantity x minus x squared to the power 1, y equals x minus x squared quantity to the power 2, y equals quantity x minus x squared to the power 3, and so on, taken between the limits x equals 0 and x equals 1, and shows that the areas are respectively 1, 1 over 6, 1 over 30, 1 over 140, and so on. He next considers the curve of the form y equals x to the power 1 over m, and establishes the theorem that the area bounded by the curve, the axis of x, and the ordinate x equals 1 is to the area of the rectangle on the same base and the same altitude as m over m plus 1. This is equivalent to finding the value of the integral from 0 to 1 of x raised to the power 1 over m dx. He illustrates this by the parabola in which m equals 2. He states, but does not prove, that the corresponding result of the curve of the form y equals x raised to the p over q. This work contains also one of the earliest investigations of the formation and properties of continued fractions, a discussion that was suggested by Bruckner's use of these fractions. Wallis shewed considerable ingenuity in reducing the equations of curves to the forms given above, but as he was unacquainted with the binomial theorem he could not effect the quadrature of the circle whose equation is y equals quantity x minus x squared to the half, since he was unable to expand this in powers of x. He laid down however the principle of interpolation. Thus, as the ordinate of the circle y equals x minus x squared raised to the half is a geometrical mean between the ordinate of the curve y equals quantity x minus x squared raised to the 0 and y equals quantity x minus x squared raised to the 1, it might be supposed that as an approximation the area of the semicircle, the integral from 0 to 1 of quantity x minus x squared dx, which is 1/8 pi, might be taken as the geometrical mean between the values of the integral from 0 to 1 of quantity x minus x squared raised to the 0 dx and the integral of 0 to 1 of quantity x minus x squared raised to the 1 dx, that is, the values 1 and 1/6. This is equivalent to taking 4 multiplied by the root of 2/3, or 3.26 approximately, as the value of pi. But Wallis argued we have in fact a series 1, 1/6, 1 over 30, 1 over 140, and so on, and therefore the term interpolated between 1 and 1/6 ought to be so chosen as to obey the law of the series. This, by an elaborate method which I need not describe in detail, leads to a value for the interpolated term which is equivalent to taking pi equals 2 times 2 over 1 times 2/3 times 4/3 times 4/5 times 6/5 times 6 over 7 times 8 over 7 times 8 over 9, and so on. The subsequent mathematicians of the 17th century constantly used interpolation to obtain results which we should attempt to obtain by direct analysis. A few years later, in 1659, Wallis published a tract containing the solution of the problems on the cycloid which had been proposed by Pascal. In this he incidentally explained how the principles laid down in his Arithmetica Infinitorum could be used for the rectification of algebraic curves, and gave a solution of the problem to rectify the semicubal parabola x cubed equals ay squared, which had been discovered in 1657 by his pupil William Neal. This was the first case in which the length of a curved line was determined by mathematics, and since all attempts to rectify the ellipse and the hyperbola had been necessarily ineffectual, it had been previously supposed that no curves could be rectified, as indeed Descartes had definitely asserted to be the case. The cycloid was the second curve rectified, and this was done by Wren in 1658. Early in 1658 a similar discovery, independent of that of Neal, was made by Van Heuraet, and this was published by Van Schooten in his edition of Descartes Geometrica in 1659. Van Heuraet's method is as follows. He supposes the curve to be referred to rectangular axes. If this be so, and if xy be the coordinates of any point on it, and n the length of the normal, and if another point whose coordinates are x nu to be taken such that nu to h equals the ratio n to y, where h is a constant, then if ds be the element of the length of the required curve, then we have by similar triangles the ratio ds to dx equals n to y. Therefore HDS equals nu dx. Hence, if the area of the locus of the point x nu can be found, the first curve can be rectified. In this way Van Heuraet effected the rectification of the curve y cubed equals ax squared, and added that the rectification of the parabola y squared equals ax is impossible, since it requires the quadrature of the hyperbola. The solutions given by Neal and Wallis are somewhat similar to that given by Van Heuraet, but no general rule is enunciated, and the analysis is clumsy. A third method was suggested by Fermat in 1660, but it is both inelegant and laborious.
In 1665 Wallis published the first systematic treatise on analytical conic sections. I have already mentioned that the Geometrie of Descartes is both difficult and obscure, and to many of his contemporaries to whom the method was new it must have been incomprehensible. Wallis made the method intelligible to all mathematicians. This is the earliest book in which these curves are considered and defined as curves of the second degree, and not as sections of a cone on a circular base. The theory of the collision of bodies was propounded by the Royal Society in 1668 for the consideration of mathematicians. Wallis, Wren, and Huygens sent correct and similar solutions, all depending on what is now called the conservation of momentum. But while Wren and Huygens confined their theory to perfectly elastic bodies, Wallis considered also imperfectly elastic bodies. This was followed in 1669 by a work on statics, centres of gravity, and in 1670 by one on dynamics. These provide a convenient synopsis of what was then known on the subject. In 1685 Wallis published an algebra preceded by a historical account of the development of the subject, which contains a great deal of valuable information. The second edition, issued in 1693 and forming the second volume of his opera, is considerably enlarged. This algebra is noteworthy as containing the first systematic use of formulae. A given magnitude is here represented by the numerical ratio which it bears to the unit of the same kind of magnitude. Thus when Wallis wants to compare two lengths he regards each as containing so many units of length. This perhaps will be made clearer if I say that the relation between the space described in any time by a particle moving with uniform velocity would be denoted by Wallis by the formula S equals vt, where S is the number representing the ratio of the space described to the unit of length, while previous writers would have denoted the same relation by stating what is equivalent to the proportion S1 over S2 equals V1T1 over V2T2. See for example Newton's Principia, book 1, section 1, lemma 10 or 11. It is curious to note that Wallis rejected as absurd the now usual idea of a negative number as being less than nothing, but accepted the view that it is something greater than infinity. The latter opinion may be right and consistent with the former, but it is hardly a more simple one. Fermat. While Descartes was laying down the foundation of analytical geometry, the same subject was occupying the attention of another and hardly less distinguished Frenchman. This was Fermat. Pierre de Fermat, who was born near Montauban in 1601 and died at Castres in January 12, 1665, was the son of a leather merchant. He was educated at home. In 1631 he obtained the post of councillor for the local parliament at Toulouse, and he discharged the duties of the office with scrupulous accuracy and fidelity. There, devoting most of his leisure to mathematics, he spent the remainder of his life, a life which, but for a somewhat acrimonious dispute with Descartes on the validity of analysis used by the latter, was unruffled by any event which calls for special notice. The dispute was due chiefly to the obscurity of Descartes, but the tact and courtesy of Fermat brought it to a friendly conclusion. Fermat was a good scholar and amused himself by conjecturally restoring the work of Apollonius on plane loci. Except for a few isolated papers, Fermat published nothing in his lifetime, and gave no systematic exposition of his methods. Some of the most striking of his results are found after his death on loose sheets of paper written on the margins of works which he had read and annotated, and are unaccompanied by any proof. It is thus somewhat difficult to estimate the dates and originality of his work. After his death his papers and correspondences were printed by his nephew at Toulouse in two volumes, 1670 and 1679. A summary of it with notes was published by Brazin in Toulouse in 1853, and a reprint of it was issued at Berlin in 1861. A new edition is now being issued by the French government, which will include some letters on his discoveries and methods in the theory of numbers recently found at Leyden by M. Charles Henry. Fermat was constitutionally modest and retiring, and does not seem to have intended his papers to be published. It is probable that he revised his notes as occasion required, and that his published works represent the final form of his researches, and therefore cannot be dated much earlier than 1660. I shall consider separately (1) his investigations into the theory of numbers, (2) his use in geometry of analysis and of infinitesimals, and (3) his method of treating questions of probability. 1. The theory of numbers appears to have been the favourite study of Fermat. He prepared an edition of Diophantus, and the notes and comments thereon contain numerous theorems of considerable elegance. This forms the first of 2 volumes of his works. Most of the proofs of Fermat are lost, and it is possible that some of them were not rigorous, an induction by analogy and the intuition of genius sufficing to lead him to correct results. The following examples will illustrate these investigations. A. If p be prime and a be a prime to p, then a to the power of p minus 1 subtract 1 is divisible by p. That is, when you subtract 1 from a to the power of p minus 1, this is equivalent to 0 modulus p. A proof of this, first, given by Euler, is well known. A more general theorem, that of a to the power of phi of n, subtracting 1 from that result, is equivalent to 0 mod n, where a is prime to n and phi of n is the number of integers less than n and prime to it. B. A prime greater than 2 can be expressed as the difference of 2 square integers in one and only one way. Fermat's proof is as follows. Let n be the prime and suppose it equal to x squared minus y squared, that is, to the product x plus y times x minus y. Now by hypothesis the only integral factors of n are n in unity, hence x plus y equals n and x minus y equals 1. Solving these equations we get x equals a half times n plus 1 and y equals a half times n minus 1. C. He gave a proof of the statement by Diophantus quoted above that the sum of the squares of 2 integers cannot be of the form 4n minus 1, and that he added a corollary which I take to mean that it is impossible that the product of a square and a prime of the form 4n minus 1, even if multiplied by a number prime to the latter, can be either a square or the sum of 2 squares. For example, 44 is a multiple of 11, which is of the form 4 times 3 minus 1. By 4, hence it cannot be expressed as a sum of 2 squares. He also stated that a number of the form a squared plus b squared, where a is prime to b, cannot be divided by a prime of the form 4n minus 1. D. Every prime of the form 4n plus 1 is expressible, and that in one way only, as a sum of 2 squares. This problem was first solved by Euler, who shewed that the number of the form 2 to the power m times 4n minus 1 can be always expressed as a sum of 2 squares. E. If a, b, c are integers such that a squared plus b squared equals c squared, then a times b cannot be a square. Lagrange gave a solution of this. F. The determination of a number x such that x squared n plus 1 may be a square, where n is a given integer which is not a square. G. There is only one integral solution of the equation x squared plus 2 equals y cubed, and there are only two integral solutions of the equation x squared plus 4 equals y cubed. The required solution are evidently for the first equation x equals 5 and for the second equation x equals 2 and x equals 11. This question was issued as a challenge to the English mathematicians Wallis and Digby. H. No integral values of x, y, z can be found to satisfy the equation x to the n plus y to the n equals z to the n, if n be an integer greater than 2. This proposition, known as Fermat's last theorem, has acquired extraordinary celebrity from the fact that no general demonstration of it has ever been given, but there is no reason to doubt that it is true. Probably Fermat discovered its truth for the case of n equals 3, and then for the case of n equals 4. His proof for the former of these cases is lost, but that for the latter is extant, and a similar proof for the case of n equals 3 was given by Euler. These proofs depend on shewing that if three integral values of x, y, z can be found which satisfy the equation, then it will be possible to find three and other similar integers which satisfy it. In this way, finally, we shew that the equation must be satisfied by three values which obviously do not satisfy it. Thus no integral solution is possible. It would seem that this method is inapplicable to any cases except those of n equals 3 and n equals 4. Fermat's discovery of the general theorem was made later. An easy demonstration can be given on the assumption that a number can be resolved into prime or complex factors in one and only one way. The assumption has been made by some writers, but it is not universally true. It is possible that Fermat made some such supposition, though it is perhaps more likely that he discovered a rigorous demonstration. In 1823 Legendre obtained a proof for the case of n equals 5. In 1832 Lejeune de Richelieu gave one for n equals 14, and in 1840 Lamé and Lebesgue gave proofs for n equals 7. The proposition appears to be true universally, and in 1849 Kummer, by means of ideal primes, proved it to be so for all numbers except, if any, which satisfy three conditions. It is not certain whether any number can be found to satisfy these conditions, but there is no number less than 100 which does so. The proof is complicated and difficult, and there can be no doubt is based on the considerations unknown to Fermat. I may add that, to prove the truth of the proposition where n is greater than 4, it is obviously sufficient to confine ourselves to cases where n is a prime, and the first step in Kummer's demonstration is to shew that in such cases one of the numbers x, y, z must be divisible by n.
A letter exists now in the University at Leyden which gave an idea of Fermat's methods. The letter is undated, but it would appear that, at the time Fermat wrote it, he had proved the proposition h above only for the case when n equals 3. 2. I next proceed to mention Fermat's use in geometry of analysis and of infinitesimals. It would seem from his correspondence that he had thought out the principles of analytic geometry for himself before reading Descartes' Géométrie, and had realized that from the equation, or as he calls it, the specific property of a curve, all its properties could be deduced. His extant papers on geometry deal however mainly with the application of infinitesimals to the determination of the tangents to curves, and to the quadrature of curves, and to the questions of maxima and minima. Probably these papers are a revision of his original manuscripts which he destroyed, and were written about 1663, but there is no doubt that he was in possession of the general idea of his methods for finding maxima and minima as early as 1628 and 1629.
He obtained the subtangent to the ellipse, cycloid, cissoid, conchoid, and quadratrix by making the ordinates of the curve and a straight line the same for 2 points whose abscissae were x and x minus e. But there is nothing to indicate that he was aware that the process was general, and though in the course of his work he used the principle, it is probable that he never separated it, so to speak, from the symbols of the particular problem he was considering. The first definite statement of the method was due to Barrow and was published in 1669. Fermat also obtained the areas of parabolas and hyperbolas of any order, and determined the centre of mass of a few simple curves and of a paraboloid of revolution. As an example of his method of solving these equations, I will quote his solution of the problem to find the area between the parabola y cubed equals px squared on the axis of x and the line x equals a. He says that if the several ordinates at the points for which x is equal to a times the quantity 1 minus e, and a times the quantity 1 minus e to the power of 2, and so on, be drawn, the area will be split into a number of little rectangles whose areas are respectively ae times pa squared to the power of 1/3, ae times 1 minus e multiplied by the quantity pa squared times the quantity 1 minus e squared, all under a cube root. The sum of these is p to the 1/3 a to the 5/3 times e divided by the quantity 1 minus e to the 5/3, and by a subsidiary proposition, for of course he was not acquainted with the binomial theorem, he finds the limit of this when e vanishes to be 3/5 p to the 1/3 a to the 5/3. The theorems last mentioned were published only after his death, and probably they were not written till he had read the works of Cavalieri and Wallis. Kepler had remarked that the values of a function immediately adjacent to and on either side of a maximum or minimum value must be equal. Fermat applied this principle to a few examples. Thus, to find the maximum value of x times the quantity a minus x, his method is essentially equivalent to taking a consecutive value of x, namely x minus e, where e is very small, and putting x times quantity a minus x equal to quantity x minus e multiplied by the quantity a minus x plus e. Simplifying and ultimately putting e equals 0, we get x equals half a. This value of x makes the given expression a maximum. 3. Fermat must share with Pascal the honour of having founded the theory of probabilities. I have already mentioned the problem proposed to Pascal and which he communicated to Fermat, and have there given Pascal's solution. Fermat's solution depends on the theory of combinations and will be sufficiently illustrated by the following example, the substance of which was taken from a letter dated August 24, 1654, which occurs in the correspondence with Pascal. Fermat discusses the case of two players, and supposes that the first wants 2 points to win and the second 3 points. The game will be then certainly decided in the course of 4 trials. Take the letters A and B and write down all the combinations that can be formed of 4 letters. These combinations are the following, 16 in all. Now let big A denote the player who wants 2 points and big B denote the player who wants 3 points. Then in these 16 combinations, every combination in which A occurs twice or oftener represents a case favourable to big A, and every combination in which little b occurs 3 times or oftener represents a case favourable to player big B. Thus, on counting them, it will be found that there will be 11 cases favourable to A and 5 cases favourable to B, and since these cases are all equally likely, A's chance of winning the game is to B's chances as 11 is to 5. The only other problem on this subject which, as far as I know, attracted the attention of Fermat was also proposed to him by Pascal and was as follows. A person undertakes to throw a 6 with a die in 8 throws. Supposing him to have made 3 throws without success, what proportion of the stake should he be allowed to take on condition of giving up his 4th throw? Fermat's reasoning is as follows. The chance of success is 1 in 6, so that he should be allowed to take 1/6 of the stake on condition of giving up his throw. But if we wish to estimate the value of the 4th throw before any throw is made, then the first throw is worth 1/6 of the stake. The second is worth 1/6 of what remains, that is 5/36 of the stake. The third throw is worth 1/6 of what now remains, that is 25/216 of the stake. The fourth throw is worth 1/6 of what now remains, and that is 125/1296 of the stake. Fermat does not seem to have carried the matter much further, but his correspondence with Pascal shews that his views on the fundamental principles of the subject were accurate. Those of Pascal were not altogether correct. Fermat's reputation is quite unique in the history of science. The problems on numbers which he had proposed long defied all efforts to solve them, and many of them yielded only to the skill of Euler. One still remains unsolved. This extraordinary achievement has overshadowed his other work, but in fact it is all of the highest order of excellence, and we can only regret that he thought fit to write so little. End of part 2.